Hello. So good afternoon to all of you. So our next speaker is Dr. Rakesh Kumar. Hello, sir.
Hello, sir. Hello. How are you?
Alhamdulillah, I'm fine. So we are very keen to listen to you, sir.
Thank you, sir. Thank you, sir.
Yeah. And this session will be chaired by Dr. Mubin. I think he has already joined. Yeah. Assalamu alaikum, sir.
Walaikum assalam wa rahmatullah.
So over to you, sir. Over to you. Now session is yours.
Okay, Dr. Mazid. In this session, Professor Rakesh Kumar will deliver a talk. First of all, I want to introduce Professor Rakesh Kumar. He is Associate Professor and Head in the Department of Basic and Applied Science, Punjab University, Patiala, India. Professor Rakesh Kumar is a gold medalist in MSc. He has received many academic awards like Outstanding Award, Young Geometer Award, Best Paper Presentation Award, and many more. He supervised 6 PhD scholars and publishes 72 research papers in reputed national and international mathematical journals. He has delivered about 56 invited talks in conferences, seminars, and workshops. I request Professor Rakesh Kumar to deliver his talk on the topic Geometry of Null Hypersurfaces of Lagrangian Manifolds with Rigging Technique. Professor Rakesh Kumar, please, sir.
Thank you, Dr. Muhammad Ahmed, for nice introduction for me. Before I start, I would like to thank organizer of this conference, special Dr. Majid Chaudhary ji, who give me this opportunity to share my knowledge with all of you. So just before I start, just tell me, any one of you, Doctor sir, is my page is visible here? Professor Mobin Ahmed?
Yes.
My page is visible, sir. My screen is visible, sir.
Yes, visible.
Okay, thank you very much, sir. Thank you very much, sir. So the title of my talk is Geometry of Null Hypersurfaces of Lagrangian Manifolds with Rigging Technique. Actually, this lecture is it is just an motivational lecture. In this lecture, we will discuss what is the need to discuss a rigging technique and what will happen when we use rigging technique on geometry of null hypersurfaces of Lagrangian manifolds. So these are the content of my talk. So brief introduction and motivation. So we know that a study of non-degenerate. So before I start, let me tell you there are two types of hypersurfaces and submanifolds. One is degenerate, other is non-degenerate. So degenerate means when the metric is degenerate, and non-degenerate when the metric is non-degenerate. Okay, so we know that the study of non-degenerate hypersurfaces and submanifolds of semi-Riemannian manifolds have many similarities with the Riemannian hypersurfaces and submanifold respectively. In the case when the induced metric on the submanifold is degenerate means it is null or it is like, then the study becomes more difficult and strikingly different from the study of non-degenerate submanifolds. The primary difference between the study of null submanifolds and non-degenerate submanifold is that in the first case, in case of null hypersurfaces or null submanifolds, the normal vector bundle intersects with the tangent bundle. Contrary to non-degenerate submanifolds, their tangent bundle and normal bundle, they are complementary, orthogonal and complementary to each other. But here they have some intersection with them. Thus, if M is a null submanifold of a semi-Riemannian manifold, then a vector tangent to the ambient manifold cannot, because they are intersecting, that's why a tangent vector cannot decompose uniquely into a component of tangent space and a component of normal space. This means that we cannot use the standard submanifold theory to define induced objects on null submanifold. To deal with this problem, for null hypersurfaces and submanifold, Bazanko and Duggal introduced a general geometric technique. How? By splitting the tangent bundle of the ambient space into three non-intersecting complementary, but they are not orthogonal. It is very interesting here, into vector bundles. They are three non-intersecting complementary but not orthogonal vector bundles. Two of them are null. Out of three components or three decomposition, two of them are null and one is non-null. Kupeli also deal with this problem, but in different way. Bazanko and Duggal's approach is basically extrinsic, which is comparatively very easy in contrast to intrinsic one developed by Kupeli. Our aim is to discuss the extrinsic approach given by Bazanko and Duggal. Application point of view, the geometry of null submanifolds and null hypersurfaces is needed to fill an important missing gap in the general theory of submanifolds. Moreover, growing importance of null hypersurfaces and submanifold in mathematical physics. For important point of view, for application point of view, there are two books. One by Bazanko and Duggal, which was published in 1996, and other is by Duggal and Professor Sahin. It is published in 2010. So in these books you can find loads of applications of null hypersurface and submanifolds. So their application, particularly extensive uses in relativity, make that study a topic of present scenario. So this is just a motivation. So let me introduce here very briefly about null hypersurfaces of semi-Riemannian manifolds. If M bar be a real n plus 2 dimensional semi-Riemannian manifold, where G bar is semi-Riemannian metric of constant index Q, because it has constant index, that's why this manifold M bar is never a Riemannian manifold. So let M be a hypersurface of M bar of semi-Riemannian manifold, and then you have tangent space, and we consider this as a normal space. And in case G bar is non-degenerate on the tangent space, then tangent space and normal space, they are also non-degenerate. They are non-degenerate as well as they are complementary and orthogonal subspaces of tangent bundle of tangent space of ambient manifold. This is happen in case of Riemannian submanifold or Riemannian hypersurfaces. But otherwise, when the metric is degenerate, then tangent space and normal space, they are degenerate, orthogonal, but not complementary. Clear? And consider, because they are not complementary, so that's why we have a radical space, which is the intersection of tangent space with the normal space. If this radical space is containing some non-zero vectors, then hypersurface is called null hypersurface or light-like hypersurface or degenerate hypersurface. So we have very important theorem here. This will give you the proper structure of null hypersurfaces. So if Mg, where G is the induced metric on the hypersurface, and this will be the degenerate metric. If Mg is a hypersurface of semi-Riemannian manifold, this following are equivalent. M will be a null hypersurface, and G has a constant rank M, and tangent bundle, normal bundle. This normal bundle will be a distribution on M. Since normal bundle is a distribution of M. Therefore, what will happen? Because we know that what is your radical distribution or radical space? Radical space was the intersection of tangent space and normal space. If normal space becomes a distribution, it means normal space is a part of tangent space, then it means their intersection will be equal to the normal bundle. So radical distribution is your now tangent normal bundle. And then we can consider a complementary vector bundle of radical distribution or normal distribution in Tm, and we call it as a screen distribution on M. That's why we have this expression. Now tangent bundle of a hypersurface, null hypersurface, is decomposed into a screen distribution and a normal distribution, because it is equal to actually the radical distribution. They are complementary to each other and they are orthogonal to each other also. Because induced metric G is of constant rank M, that's why this screen distribution is also non-degenerate distribution. If it is a non-degenerate distribution, we have its complementary portion. So that's why ambient manifold, tangent bundle of ambient space manifold, is equal to screen distribution and its orthogonal complementary vector bundle. Now we have very important theorem. What this theorem says, say if M is a null hypersurface of a semi-Riemannian manifold, then there exists a unique vector bundle of rank 1, and such that for every non-zero section of radical distribution, or you can say that normal distribution, what will happen? There exists a unique section N of that vector bundle which satisfies this condition. With what it means that what is happening? There is existing a unique section TR and a unique section N from TR which satisfy this condition, that G bar of N xi is equal to 1. What is xi? Xi is non-zero section of radical distribution or normal distribution. And G bar of N xi equal to 1 means this new unique distribution and normal distribution, they are not orthogonal to each other. G bar of Nn is equal to 0. It means this distribution is also a null distribution. Clear? And G bar of Nx is equal to 0, where x belongs to your screen distribution. It means your N, this new vector bundle is orthogonal to screen distribution. And we denote this new distribution, this new vector bundle, as a light-like transversal vector bundle. So hence, for any screen distribution, we have a unique this vector bundle, which is complementary vector bundle but not orthogonal to Tm. Why it is not orthogonal to Tm? Because Tm is a decomposition into radical and screen distribution, and it is known as light-like transversal vector bundle. So we have this decomposition here. That vector bundle, the vector bundle of ambient space, is equal to now screen distribution, orthogonal to both, but they are not orthogonal to each other. They are complementary but not orthogonal to each other because of this property, G bar of N xi equal to 1. Xi belongs to here, N belongs to here. This is the diagram here. So if this is the total is your tangent bundle of ambient space, then this is your tangent space, and this normal bundle is equal to radical. That's why it is, because normal bundle is your distribution, it is part of your tangent bundle, and its complementary screen distribution, and this red portion is your transversal bundle. They are not orthogonal to each other. Okay, so now if nabla bar is a Levi-Civita connection on semi-Riemannian manifold, then we have Gauss-Weingarten type formulas for null hypersurfaces, that nabla bar xy is equal to nabla xy plus bxyn, and this is what? This nabla is your induced connection on null hypersurface, and B is your local second fundamental form. And now listen very carefully. This induced connection on light-like or null hypersurface is not a metric connection. It is not a metric connection. Contrary to your general theory of submanifolds. In case of Riemannian submanifolds or non-degenerate submanifolds, your induced connection is always a metric connection. But here, this induced connection is not a metric connection. This is a major difference here. Second is this B is the local second fundamental form. It is metric always. It is AN is a shape operator of light-like hypersurface, null hypersurface. This is one form. And if you notice in the diagram, because this tangent bundle is decomposed into two orthogonal subspaces, orthogonal distribution, screen distribution and radical distribution. That's why we can also have a Gauss and Van Gatten formula for this tangent bundle also. This tangent. So let P be the projection from TM to STM. Then these are your two Gauss-Van Gatten formula for screen distribution. Here nebula star. This is your metric connection on screen distribution. So keep this in mind. This is your metric connection on screen distribution, and this is local second fundamental form for screen distribution, and it is not symmetric. So here the local second fundamental form for hypersurface, it is symmetric, but here this local second fundamental form for screen distribution, it is not symmetric. This connection, induced connection, is not metric connection, but here this nebula star induced connection on screen distribution is metric connection. So this is one difference. Moreover, this induced connection nebula satisfies this condition. So now we will discuss how some important theorems related to null hypersurfaces. So we know that any geodesic of hypersurface with respect to induced connection is also a geodesic of eminent manifold. Then hypersurface is said to be your totally geodesic null hypersurface. So using this theorem, the definition of total geodesic, we have this theorem. This theorem says if M is your null hypersurface, the following assertions are equivalent. Number one, if M is total geodesic, then your second fundamental form will vanish identically on null hypersurface. It is just equivalent to your condition of non-degenerate hypersurfaces. Here A star, which is your shape operator of screen distribution, it will vanish identically. And what will happen? This is the major component here, that the induced connection. Earlier it was a not metric connection, but when your hypersurface is total geodesic, then induced connection becomes a metric connection. That's why totally geodesic hypersurfaces are having some importance in the study of like hypersurfaces. Here normal bundle, it is parallel distribution with respect to induced connection, and it is a killing distribution also. Moreover, it is integrable also. But screen distribution need not to be integrable always. So we have a theorem that screen distribution will be integrable if and only if then local second fundamental C is symmetric. And I have already mentioned that this local second fundamental form for screen distribution is not symmetric. But when it is symmetric, your screen distribution will be integrable. And moreover, your shape operator on eminent manifold on null hypersurface, it also symmetric. So from the general theory of submanifolds, or you can say that from the non-degenerate theory of submanifolds, we know that the second fundamental form and shape operator, they are related with each other. But contrary to this, in a case of null hypersurfaces, there is an interrelation between second fundamental forms of null hypersurface and screen distribution to their respective shape operators of null hypersurface and screen distribution. Moreover, they satisfy this. What is B? This is second fundamental form of hypersurface. Second fundamental form of hypersurface is related with the shape operator of screen distribution. Second fundamental form of screen distribution is related with shape operator of null hypersurface. They are interrelated with each other. So that's why the geometry of null hypersurfaces depends upon the choice of screen distribution, which plays important role in the study of differential geometry of null hypersurfaces. That's why we are looking for one class, is that special class of null hypersurfaces whose geometry whose geometry is essentially equal to the geometry of null hypersurface, essentially equal to that of their chosen screen distribution. That we are looking for the class of those null hypersurfaces whose geometry is equivalent to the geometry of its screen distribution. And to give the answer, we have one type of special type of null hypersurfaces. Before that, we know that shape operators is an information tool in the study of geometry of some manifold. This thing we know. We are led to consider null hypersurfaces. Now we will consider those hypersurfaces whose shape operator are same as that of their screen distribution, because we have two types of shape operator for null hypersurface, shape operator for screen distribution. Now we will talk about that particular class of hypersurfaces where the shape operator of null hypersurface is conformally equivalent to the shape operator of screen distribution, and we have this definition here. A hypersurface, null hypersurface, is said to be screen conformal if the shape operator of null hypersurface is conformally equal to shape operator of screen distribution. Okay? And if where this phi is non-vanishing smooth function. If it is a non-zero constant, if phi is a non-zero constant, then it is called screen homothetic. So this theorem gives us the existence of screen conformal null hypersurfaces. In null hypersurfaces, let M be a null hypersurfaces. If the screen distribution is integrable, each leaf of screen distribution is totally umbilical, immersed in a semi-Riemannian manifold of codimension 2, with nowhere vanishing space like mean curvature vector. And if screen distribution is parallel, then null hypersurface is screen conformal. So this, it means this theorem gives us the existence of screen conformal null hypersurfaces. Now, what is the use of this screen conformal null hypersurfaces? Due to the problem, the major problem is the degeneracy of induced metric on null hypersurface. Due to the degeneracy of induced metric on null hypersurface, the screen distribution, which is not degenerate, we already mentioned, screen distribution is not unique. The screen distribution is not unique. Since 1996, considerable work has been done in the search of unique screen distribution. Kupeli also showed, although screen distribution is not unique, but it is canonically isomorphic to factor bundle. So using this technique, replacing screen distribution by factor bundle, it leads to intrinsic geometry. But we are interested in extrinsic geometry only. So which is because extrinsic geometry is in the line of non-degenerate theory of some manifolds. So that now we have one definition, which is first derivative. The first derivative of screen distribution is spanned by Lie brackets of x and y vectors, where x and y are screen distribution, and omega is one form which is geometrically equivalent to a vector of screen distribution. Now we have this theorem. This theorem gives us why screen conformal, light-like hypersurfaces are more important. If M is a screen conformal null hypersurface of a semi-Riemannian manifold with S1 as a first derivative of screen distribution, then what happens? Your screen distribution will be integrable. One form vanishes totally on first derivative. If first derivative coincide with screen distribution, then M, null hypersurface, can admit a unique screen distribution. The major problem with the theory of null hypersurfaces was screen distribution was not unique, and this class of screen conformal null hypersurfaces gives us that screen distribution is unique. That's why this class is very important. If we denote R02 as a 0-2 tensor on null hypersurface defined by this, and after simplification we get this expression of R02 in terms of Ricci bar. This Ricci bar is a Ricci tensor of ambient manifold. This B is a local symmetric, local second fundamental form. Clear? If you notice in this expression, we know that Ricci bar is symmetric always. This local second fundamental form is symmetric, but this is not symmetric and this is not symmetric. So conclusion is this 0 to tensor is not symmetric. If it is not symmetric, then it is just a tensor quantity. It has no physical or geometrical meaning as compared to contrary to symmetric Ricci bar. That's why we define this definition. We call this R02 as a induced Ricci tensor if it is symmetric. Otherwise, it is simple tensor. When it becomes symmetric, only then we will say it as a induced Ricci tensor. This is another difference between non-degenerate theory of some manifolds and null geometry of hypersurfaces. That in case of non-degenerate theory of some manifolds or hypersurfaces, induced Ricci tensor is always symmetric, but here it need not to be symmetric always. But when we take a class of screen conformal null hypersurfaces on real space form, then this R02 tensor becomes symmetric. It means this tensor becomes induced Ricci tensor. As I already mentioned, totally geodesic null hypersurfaces are also very important because totally geodesic null hypersurface generates a metric connection on induced metric connection on null hypersurfaces. That's why if your M is and a hypersurface is totally geodesic, then your this tensor 0 to 2 tensor is also symmetric, means it also becomes a induced Ricci tensor. So this is brief about the theory of null hypersurfaces. So what is the conclusion here? In case of in case of null hypersurfaces, the conclusion is since both null section and screen distributions are fixed arbitrarily, independent, how to choose them? So that's why it is it is not clear how to choose them. So that's why in order to have reasonable coupling between the properties of null hypersurface, it create a problem to us. Moreover, screen distribution is not unique. Moreover, induced connection is not a metric connection. Induced metric is not a non-degenerate metric. So all these that's why it is not a appropriate tool to study intrinsic geometry of null hypersurfaces. Despite of limitation, it has great success. So now we will discuss null hypersurfaces with rigging. So Guriraj and Ulia presented new rigging technique to study null hypersurfaces of Lorentzian manifold. So what is rigging technique? There are two major applications of rigging technique. First is this earlier our geometric data is depending upon two objects, screen distribution and null distribution. But here your geometric data will depend upon only one unique object, that is called rigging vector field. And secondly, secondly, a Riemannian structure. Riemannian structure will introduce on null hypersurface. This is the major important. So rigging technique is based on arbitrary choice of transverse vector field, that is called rigging vector field, from which we can construct a null section, and that is called rigged vector field, and a screen distribution. So it means now we need only one unique section, unique vector field, that is called a rigging vector field. Using this rigging field, we can construct a null section, and we can construct a screen distribution. So now our geometric data is depending upon only a unique object. And the major advantage of rigging technique is on null hypersurface. On null hypersurface, it allows us to construct a Riemannian metric. It means on null hypersurface, along with the degenerate metric, we can introduce a Riemannian metric, that is called rigged metric. And now data will be depending upon a unique object. So when you have a Riemannian metric on null hypersurfaces, now you can use the theory of Riemannian manifold to study null hypersurfaces. So this is the major application here. So if M is a null hypersurface of Lorentzian manifold, alpha is a one form geometrically equivalent to zeta, where zeta is a vector field defined in some open subset containing null hypersurface. Now we consider this tensor G hat, which is G bar plus alpha cross alpha, and this is G tilde. This is G tilde is pullback or induced metric, which is G plus omega cross omega. So we have this lemma. This lemma says this G hat, this new metric, this G hat is degenerate if your zeta, which is in some open set containing hypersurface, null hypersurface, is G hat is degenerate if zeta is time-like and geometry. And we have this important result, very important result, that the induced metric, induced from this new metric G hat, this new metric G tilde is Riemannian. This will be Riemannian if zeta does not belongs to the tangent space of null hypersurface. So using this condition, we define we define the definition of rigging vector field. M is a null hypersurface. A rigging will be a vector field zeta, which does not belongs to the tangent space of the null hypersurface. So it means using this condition, what will happen? Your induced metric G tilde will be the Riemannian metric, and this metric is called rigged metric. Clear? And this using rigged metric, we have a rigged vector field also. Rigged vector field is induced from a rigging zeta, which is G tilde metrically equivalent to one form omega. That is, omega will be equal to G tilde this, and this is denoted by xi also. And if you notice, this rigged vector field is G tilde unitary, and this rigged xi is also unique null vector field for M also, which satisfy this condition. So then we find then using this rigging, we can find a screen distribution, and we are denoting it by S zeta because it is depending upon zeta, and it is should be noted that screen distribution is G tilde orthogonal subspace to rigged vector field. And using this rigged vector field, we can define a null transversal vector field by this, and which satisfy this condition, of course. So a null hypersurface with rigging is called normalized null hypersurface, and normalized hypersurface is called closed when one form is closed or rigging is closed, and it is called conformal when rigging is conformal. So using this particular condition, that if M is a null hypersurface and this zeta, this your rigging vector field is a closed rigging, then we have these two this definition, these two equations. If you notice very carefully, these are your Gauss-Weingarten type formulas on null hypersurfaces, and where nabla tilde, it is a connection induced by a rigged metric G tilde, and it is a Levi-Civita connection. Why a Levi-Civita connection? Because G tilde is a Riemannian metric here. So now we have separately, now on a single null hypersurface, we have two connections. One is induced from nabla bar, which is not a metric connection. Other is induced this connection nabla tilde, which is Riemannian connection. We have two metrics on null hypersurface. One is degenerate metric, other is G tilde, which is a Riemannian metric. So what is the conclusion here? So we all of us know about Riemannian geometry of submanifolds and hypersurfaces. So now we can use the geometry of Riemannian submanifold and hypersurfaces to study the geometry of null hypersurfaces, because now we have so in some papers you can find a interrelation between them also. So this is the conclusion here. So we in next section we introduce null rigging technique on Hermitian manifold also. So if M is a null hypersurface of an almost Hermitian manifold, we define a rigging zeta which is called compatible with indefinite almost Hermitian structure if G tilde G bar of zeta with G xi equal to 0. So we denote it by J rigging, which satisfy these conditions. So this conditions gives you ultimately what happens. So this diagram is, this is your tangent space, This is your tangent space of null hypersurface. This is your light-like transversal bundle, and this is your radical space. And now we have almost complex structure J, because your rigging is compatible. Your rigging is compatible with indefinite almost Hermitian structure. That is, it is satisfying this. Then by using these equations, what happens that the image of light-like transversal vector bundle with J also belongs to screen distribution. The image of radical distribution or normal distribution also belongs to your screen distribution under J. And we have this D. What this D is, this D is almost complex distribution. It is complex. So this is the decomposition of tangent space of eminent manifold. So then we defined a associated metric G hat on M bar by this. If you notice, we proved that this G hat is a non-degenerate metric. It is a non-degenerate metric if G bar of zeta is equal to -1. And if you notice, this G hat satisfies JU JB is equal to G hat of UB. So that's why we denote it as associated almost Hermitian structure on M bar, where M bar is almost Hermitian manifold. So it means now on an almost Hermitian manifold, now we have two structures. One is G bar J and other is G tilde J. So we take pullback, we take induced metric on null hypersurfaces through G hat, so which is equal to this. And you notice we have this theorem that this G tilde metric is non-degenerate on null hypersurface. In case of last section, when our ambient space is Lorentzian manifold, your G tilde metric was Riemannian. Here, in case of indefinite almost Hermitian manifold, our induced metric G tilde on null hypersurface is non-degenerate. So we take nebula bar and nebula hat are Levi-Civita connections, clear? Because it is G tilde, G hat is non-degenerate. That's why we have a Levi-Civita connection. So on two indefinite almost Hermitian manifolds, say they satisfy this condition, and this further can be written to this form. So from here it is very much clear that if M bar is scalar with respect to G bar, then it is not scalar. If it is scalar with respect to G hat, and then this is not scalar. So that's why we have this theorem. It is very important theorem that the structures G bar J and G hat J are not simultaneously scalar. If M bar is your scalar manifold, then this previous expression further can be simplified into this way in terms of nebula bar of alpha. By direct simplification, we know this result. If this alpha, one form alpha is parallel, then it means if and only if this zeta is killing, and zeta it is closed. So using this property, we have this very important theorem. This theorem says if rigging is closed and killing, it gives you this is as a 0, it is alpha is a parallel. Then using here this manifold M bar with this structure becomes scalar. So this theorem says that if M bar is a scalar manifold, if zeta is closed killing, then this structure is also scalar. So concircular vector field we know. So this is okay, no problem. Now this is very important theorem. If M bar is your indefinite scalar manifold with closed killing rigging, it means now we are choosing particular rigging which is closed and killing. Then we have these Gauss and Weingarten formulas for null hypersurfaces. Clear? So using these Gauss and Weingarten formulas, now we can study null hypersurfaces with the help of non-degenerate hypersurfaces. So this is okay. Now using these calculations, we find the expression of induced Ricci tensor, which becomes symmetric, and then we find the expression of scalar curvatures. this is scalar curvature induced on null hypersurfaces with rigging curvature, and this is scalar curvature of an almost compressed space form. This is a relation between them, and further lot of theory can be generated in this way. So last, I take very few more minutes. So we can also generalize the concept of rigging technique on generalized Walker space-time, Robertson-Walker space-time. This we know what is generalized Robertson-Walker space-time. This is wrapped product manifold. Clear? With this as a Lorentzian manifold. Clear? So then any vector field U can be written to this form, because where this delta T is your, it is lift of a standard vector field on open interval I. Okay? So
मैं ये डॉक्टर साहब से पूछ रहा था
using this
जो यूनिवर्स
condition,
के मोबाइल
this
नंबर तक
result
होना
is very
जरूरी है क्या?
obvious.
तो अगर नहीं है कुछ तो मिल जाते हैं भाई, उनके उस पे ऑफिस वगैरह कुछ लोग डाले होते हैं.
So B.Y. Chan proved that a Lorentzian manifold is a, because this B.Y. Chan gives a local characterization of a Lorentzian manifold to be a GRW space.
How one?
No, it is request to my audience, please mute yourself. I will take only 1 or 2 minutes more, please.
नहीं भाई, पॉसिबिलिटी है कि जो कुछ लोगों का होता है ना, मिल जाता है ना.
Please, audience, please mute yourself. Audience, please mute yourself so that I can complete within 2 minutes. Okay. So B.Y. Chan give a very nice characterization that a Lorentzian manifold will be a generalized Robertson vector space-time if it admits a time-like cone circular vector field. And Chen showed that this rho delta T is the required time-like cone circular vector field. So we choose this as our rigging vector field. And using this as a rigging vector field, then we find associated null transversal vector field in this form. And using in generalized Robertson vector space-time, we have astonishing family of space-like hypersurfaces, which are slices of space, which are space-like slices. Clear? So in case of generalized Robertson vector space-time, a U can be written in this form. So now, if psi is a vector mapping from F to R, F is over fiber for generalized Robertson Walker space-time. Let M be a graph of this function. Then the graph of this function will be a null hypersurface. The graph of this function psi will be a null hypersurface of a generalized Robertson Walker space-time. If I now live, then it satisfies this condition. So it means our graph of a function on a fiber becomes a null hypersurface. So let X be any element from the fiber. We define a level hypersurface of the fiber. Clear? Because it is a hypersurface, it is dimension n. Then we have E1 to En are orthonormal frame field.
Hello. I think there is some technical problem, and Rakesh sir has just joined. He's disconnected now.
Okay, Majid, wait 2-3 minutes.
Yeah. We can wait.
Sorry. Hello. Am I audible?
Yes, now you are audible.
Sorry, it was light. Due to technical issue, light was off here. So I think my time is over. The last topic is just to how to introduce your rigging technique or generalized operational worker space time. If anyone is interested, I can share my PPT with those candidates also. So only in one line, one minute, only in 1 minute. So using we are defining rigging technique on a null hypersurface, which is a graph of a function on a fiber. So I am just going the result here. So using here, so finally we derived the relationship between scalar curvature of normalized hypersurface in terms of scalar curvature of the fiber, and finally we find this condition also that this normalized scalar curvature of normalized hypersurface will be 0 if m bar is Minkowski space. The expression for scalar curvature for normalized hypersurface will be this if m bar is de Sitter space and it is for anti-de Sitter space. So these are the references which we have used. So thank you very much.
So, Professor Rakesh Kumar was delivered a very nice lecture on geometry of null hypersurfaces of Lorentzian manifolds with rigging technique. Although this rigging technique was not so easy technique, but he presented in the way that it becomes very clear to all of us. Audience, if you have any query, then you can ask Professor Rakesh Kumar. Professor Rakesh Kumar.
Yes, sir.
One query from my side. What about the totally geodesic and totally umbilical hypersurface definitions when we use rigging technique? If it is remain same or this?
Yes, they remain same. They remain same.
They remain same.
Actually, definition of totally umbilical and total geodesic.
Because there are two metric used. In that sense, I say, if there is any difference.
Actually, the only difference is, listen, when we are talking about definition of totally umbilical in case of null submanifolds. Clear? In case of null submanifold, what happens? The second fundamental form is decomposed into two portions. One is from transversal screen distribution and other is light-like transversal vector bundle. So it will be totally umbilical if the screen transversal vector bundle, component of screen transversal vector bundle and component of light-like transversal vector bundle, they satisfy the same condition of umblicity, which we have the definition for umblicity for non-degenerate submanifolds. So this is the minor difference here. That the rest of is same, exactly same.
Okay.
May I have a question, please?
I think that this null hypersurfaces does not applicable in case of the Riemannian manifold.
Sorry, pardon. Repeat your question, please.
Null hypersurfaces can be applicable in case of the Riemannian manifolds.
No. Listen.
This is semi-Riemannian manifold.
Yeah, exactly. When the ambinate manifold is semi-Riemannian, when ambinate manifold is Riemannian, it will induce Riemannian manifold always. When the ambinate manifold is semi-Riemannian, it may induce non-degenerate, it may induce degenerate. So we have two different categories here.
Excuse me, I'm sorry.
Question, please.
I'm sorry, but we are already 10 minutes late, and our next speaker, Professor Adela Mihai, is waiting. So,
okay, that's fine.
So I will appreciate if you directly ask the question to Dr. Rakesh Kumar. I'm sorry.
Thank you, Majidi. Thank you for giving me this opportunity.
Okay,
And I also wish good luck to Professor Adela Mihai for her presentation and her talk.
Okay. Rakesh sir, you can directly contact Professor
Okay,
Bel
thank
Khalfa.
you.
He wanted to ask some question.
Sure, sir. Sure, sir. Thank you, sir. Thank
Professor
you, sir.
Bel Khalfa, I'm really sorry, but we are actually 10 minutes late.
It's okay. It's okay. It's good to hear also our colleague Adila.
Yeah. If you want to ask any question, you can directly ask to Professor Rakesh Kumar. Okay, thank you everyone. And yeah, our next speaker is Adela Mihai, Professor Adela Mihai from Romania, and she is already here. So I would, on behalf of Department of Mathematics, School of Sciences, Manu Hyderabad, and on behalf of organizing committee, I welcome you, Professor Adela, here. And before you start, I would give you a brief introduction of Professor Adela. Professor Adela, her affiliation is from Technical University of Civil Engineering, Bucharest, Department of Mathematics and Computer Sciences, Romania. And she did her bachelor's and a master's and from Bucharest University, Romania, and her PhD from Al-Iqza University, Romania. So currently she is serving as associate professor in the Department of Mathematics, Faculty of Maths and Computer Science, University of Bucharest from 2016 onwards. And her research interests are submanifold theory in complex manifolds and invariant theory, submanifold finite type, applications of differential geometry in economics, and statistical manifolds. She has won many prizes, and not to there are so many, and there are so many scores and grants she has received. So I'm unable, due to shortage of time, I'm unable to read out all those prizes and grants. And she has published a number of papers in reputed journal of high index in SCI journals, and she has presented her work. She has delivered a number of invited talks globally. So on behalf of organizing committee, I welcome you, ma'am, here. And now over to you, ma'am. It's your session now.
Thank you very much. I'm very glad to be here and to see so many friends. Please confirm you can see my screen if possible.
Yeah, ma'am. Yeah, ma'am. It's visible, okay. Ma'am.
Yeah. Okay. So thank you for the presentation. And my talk today will be on rectifying curves. Yes, I'm from Technical University of Civil Engineering, Bucharest, Romania. And also I am a PhD supervisor at Transylvania University of Brașov, Romania. So I also thank the organizers because they admit our PhD students to take part of this conference. So this is a joint work with my colleagues from Technical University of Civil Engineering, Bucharest. Let me say their names: Marilena Gianu, Severa Chimescu, Leonard Dăuș, Olimpia Alice Roman is our student, she is our master student, and Daniel Tudor. And founder, as found, we have an internal project, very short, 4 months long project last year, sponsored by our university. Let me start with a presentation of my talk. What a rectifying curve is. A rectifying curve is a twist curve. By a twist curve, we mean a curve which has non-zero curvature and torsion, with the property that all its rectifying planes pass through a fixed point. If this fixed point is exactly the origin of the Cartesian coordinate system, then the position vector of the rectifying curve always lies in the rectifying plane. A remarkable geometrical property of these curves is that the ratio between torsion and curvature is a non-constant linear function of the arc length parameter. In this talk, first, we give a new characterization of rectifying curves by involving the involute and the evolute of the curve. We present an example of a rectifying curve obtained as the evolute of a spherical helix, and we also express the curvature and the torsion of a rectifying spherical curve and give necessary and sufficient conditions for a curve and its involute to be both rectifying curves. What we know until now. So the term rectifying curve was introduced by Bang and Chen in 2003 in the American Mathematical Monthly in a very nice paper entitled "When does the position vector of a space-time of a space curve always lie in its rectifying plane?" In that paper, Chen called a rectifying curve a curve whose position vector always lies in its rectifying plane. We all know this picture. We have the Frenet triedron, tangent line, principal normal line, binormal line, and of course, osculating plane spanned by tangent and principal normal, normal plane spanned by principal normal and binormal, and rectifying plane, which is the hero of our talk, which is spanned by the tangent line and the binormal line. Here is a rectifying plane spanned by T and B. Let's suppose that this is the origin of the coordinate of our system, Cartesian system. This is the position vector, and this is a rectifying plane. Then, if rectifying plane of all points on the curve pass through this origin, then what we obtain here, it's a rectifying curve. Other known results. There is a paper previously published than the paper of Chen by Kim, Chung, and Cho, entitled Space Curves Satisfying Tau over K, torsion over Tau over K equal AS plus B over curvature, which is a linear function. So in this paper, the author studies the property of space curves satisfying Tau over K equals AS plus B. And they proved that a curve has this property if and only if there exists a point such that all the rectifying planes to the curve pass through this point. By a translation, any curve of this type turns to be a rectifying curve in the sense defined by Bang and Chen. And in this study, in this paper, we use the definition of rectifying curve, this definition of the authors Kim, Chang, and Cho, because it's a bit general, more general than the definition given by Bang and Chen. The geometric properties of rectifying curves are presented in details in two very nice papers. First, is the paper I already mentioned, in which Bang and Chen introduced his notion of rectifying a space curve. And the other one is a paper of Chen and Dillon, Rectifying Curves as Centroids and Extremal Curves, published in 2005. Very nice result, simple, but very nice and very geometrical result. It is shown in both papers that any rectifying curve has a parametrization of this form. So we can write x of t as a secant t plus t0 times y of t, where this y is a unit speed curve on the unit sphere S2. A is a positive constant, T0 is another constant. So this is very important. We know, we have an idea how we can we give a parametrization, I'm sorry, for a rectifying curve. There is another paper published by Bang and Chen in 2007, where he proved that a geodesic on a conical surface is either a rectifying curve or an open portion of a ruling. Please keep in mind this result because we come back to this at the end of the talk. The relationship between rectifying curves and the notion of centroids in mechanics was pointed in the paper of Chen and Dillon 2005, I already mentioned, and also was developed by Deschmuth, Chen, and Al-Shamari in 2018 in Turkish Journal of Mathematics in the paper with the title on rectifying curves in the Euclidean tree space. The centroid of a curve is the curve defined by the Darboux vector, which is torsion tau plus curvature b. The authors proved that the centroid of a unit speed curve with constant non-zero curvature and non-constant torsion is a rectifying curve. And also the same result is true for a curve with constant non-zero torsion and non-constant curvature. And the generalization of these results is given in the paper of Deschmuth and the other authors in 2018, where it was proved that the centroid of a twist non-helical curve is a rectifying curve if and only if the curvature k and the torsion tau are not both constants, and moreover, if they satisfy a very nice non-homogeneous linear equation of this form, ak minus b tau equals c, where a, b are such that a squared plus b squared non-zero and c is not zero. Also, for any twist non-helical curve, the dilated centroid, which is defined by 1 over k times the Darboux vector, is also a rectifying curve. Now, let me start with some preliminaries, only to fix the notations, because we all know very well those notions. So, we denoted by E3 the Euclidean tree space. Let I be a real interval and X a space curve parameterized by arc length S. Then the unit vector field T, derivative of X, is the tangent vector field. The curvature of the curve X is the positive function, norm of derivative of T. And the principal normal vector field is defined as T derivative of T over K. Is it immediately that n is orthogonal to the tangent. And of course, the binormal vector field is the cross product time T times n. The torsion of the curve is given by the equation derivative of b equals minus tau n. And in fact, I'm going to recall the well-known Frene formulas. So the vectors t, n, and b satisfy the following Frene-Serre formulas. Derivative of t equals kn, derivative of n equals minus kt plus tau b, derivative of b equals minus tau n. And as we already show in the picture, the planes determined by Tn, Tb, and Nb are respectively called the osculating plane, the rectifying plane, and the normal plane. In the following, we start with x, a unit speed curve of non-zero curvature. A curve x is a rectifying curve if there exists a point x0 which belongs to all the rectifying planes to the curve. Chen later, after his initial definition of rectifying curve, he said such a point x0 which is common to all the rectifying planes and is uniquely determined is said to be the reference point of the rectifying curve. Then, by previous definition, how can we write a rectifying curve? It's very simple. X of s equals, this is the reference point, plus lambda t plus mu b, where of course lambda and mu are functions of C infinity class. But this function cannot be arbitrary, and they have a well-defined form established by the following theorem given by Chen and also given by Kim et al. Previously in 10 years before Chen. So, more precisely, the unit speed curve x is a rectifying curve if and only if there exists a fixed point x0 and constants nu and mu non-zero, such that one can write x equals x0 plus s plus nu times t plus mu b. So the function mu of s is in fact a constant, and the function lambda of s is a linear function on the form s plus a constant mu. This is very useful shape of a unit speed curve which is rectifying. But as we already said, a rectifying curve can be also defined by the ratio tau over k. We all know that a space curve is said to be a generalized helix if and only if this ratio is a non-zero constant. But for rectifying curves, the ratio must be a non-constant linear function of arc length s. We just differentiate the shape of our rectifying curve and use Frene-Serre formula. So we obtained that in fact tau over k can be written as 1 over mu s plus nu over mu. Then we have the following theorem, which is completely proved in paper of Chen. The unit speed curve x is a rectifying curve if and only if there exist constants alpha and beta, such that the ratio can be written as alpha s plus beta. The following theorem gives us necessary and sufficient conditions for a rectifying curve to lie on a sphere. More precisely, a unit speed rectifying curve lying on a sphere of radius r has the curvature and torsion expressed by the relations 7 and 8. And it's nice because we also have the converse statement. So conversely, if the curvature and torsion of a curve are given by 7 and 8, then this curve is a spherical rectifying curve. Of course, one can see that the ratio here, tau over k, is exactly alpha s plus beta. The proof is not complicated. We just used the fact that the x is a unit speed rectifying curve which lies on the sphere of radius r. We differentiate the relation above and use Frenet-Serre formulas. I am not going inside the proof very deep. What we've got, in fact, we obtain this equation. And from here, of course, we obtain expression of the curvature. And quickly, we obtain the expression of the torsion. And conversely, if x is a curve with the curvature k and torsion tau given by those two formulas, then one can verify that k and tau satisfy this equation. And this is it's quite well-known relation for a curve which lies on a sphere of radius r. So for example, I give this reference. So we prove that if k and tau have the shape given by the formula 7 and 8, then the curve x lies on a sphere of radius r. Let me recall now a few things about an involute of a rectifying curve. So an involute of a curve x is a curve y lying on the surface generated by the tangent lines to x and having the property that these tangent lines are orthogonal to the corresponding tangent lines to y. So I just took a small picture from the definition of involute given by in this book. Is a very nice book we use very often also for our students. So we have a curve here. We take the tangent lines, they form a surface. Then on this surface, we take a curve with the property that the tangents of the second curves are orthogonal in corresponding points, let's say, to the tangent of the first curve. So in this case, we know that C star, as is denoted here in the photo, we call it Y, is the involute of C. So Y is the involute of X, having the property that the tangents are orthogonal. And it's not difficult to prove that the involute has this very simple form, y equals x plus c minus s t. So this is the relation between curve and its involute. Now let's consider that our curve is a rectifying curve. And we thought, okay, what happens now with its involute? And we prove the following theorem. Any involute of a rectifying curve lies on a sphere centered at the reference point. So we prove that any involute of a rectifying curve is a spherical curve. And the center of the sphere is exactly the reference point of the rectifying curve. So let me recall, the reference point was the common point of all the rectifying planes. And the next theorem established in which conditions an involute of a rectifying curve is also a rectifying curve. So let X be a rectifying curve. Then this is Y, her involute. Y is also a rectifying curve if and only if the curvature, but please pay attention that this is the curvature of the initial rectifying curve, is expressed by this relation. It does not look so nice, but in fact is not so complicated, because all we needed to know is to express the relations between the Frenet trihedron of both curves. So we found that if the Frenet frame of the initial rectifying curve is T and B, then the Frenet trihedron of the involute is T tilde, N tilde, B tilde, having these expressions. And it's easy, very, very easy to see that T tilde is exactly N. So in fact, they have common tangent and normal. So those are the relations. We also express K tilde and tau tilde with respect to tau and K. We use the fact that X is a rectifying curve, and then we arrive at the following differential equation. But this is nice because it's a Bernoulli differential equation. So by solving by hand, we solve this Bernoulli differential equation. So we found the general solution of this is the expression of K. Also, if we look at this formula, what we can see, because tau over K is not 0, then tau tilde cannot be 0. So we conclude that rectifying curve is always a that the involute of a rectifying curve is always a non-planar curve. Moreover, but here I did not write the proof, can be proved that if a rectifying curve X has an involute Y, which is a rectifying curve, why I say an involute? Because we all know that a curve has many involutes. But if one is a rectifying curve, then any other involutes of X are not rectifying curves. Also, if the curve X and its involute are both rectifying curves, they cannot have the same reference point. So the point where are common for the rectifying planes, because both are rectifying now, cannot coincide. And here is the proof, but I'll go further. Okay, what an involute of a curve is? We all know that an involute of a curve Y is a curve X with the property that Y is an involute of X. So we know that evolute and involute are pair curves. And here is the photo for the evolute. So if a curve C is an involute of C star, then C star is the evolute of C. Also, in this case, we can express X star, which denotes C star via X. So more precisely, the evolute of a curve Y can be written as X equals Y plus 1 over K tilde times N tilde minus tangent of T, B tilde. T is a primitive of the torsion tau tilde. The calculations are not very difficult and can be found in some books in differential geometry of curves as well. So it's important that we know how to express the evolute with respect to the initial curve. So we point out that if the evolute x of a curve y is a rectifying curve, then y must be a non-planar curve that lies on a sphere centered as a reference point of x. And in the next theorem, we prove that any evolute of any spherical non-planar curve is a rectifying curve. The evolutes of a spherical non-planar curve are rectifying curves, again with the reference point at the center of the sphere. I'll not go into the proof, but as a corollary, I'd like to mention that a curve x is a rectifying curve if and only if it has a spherical involute. So this, in fact, is a new characterization of a rectifying curve, this corollary. And in this case, the reference point of x is the center of the sphere. This is a spherical involute. And all the involutes of x lie on concentric spheres centered at this point. So only the radius are different for the other involutes. All are spherical, and the center of the sphere is the same. So, because of this characterization we obtained, we are now able to construct some rectifying curves. Until this characterization of rectifying curves via its involutes and evolutes, there were two main sources for the construction of rectifying curves. More precisely, we knew until now to construct them as dilations of unit speed spherical curves or as dilated centroids of some type of curves. Could you please ask our colleagues to switch off the microphone?
எக்ஸ்டர்னல் ஒரு கொஸ்டின் பேப்பர் எடுப்பாங்க வேற காலேஜ்ல இருக்கிறோம் அந்த ரெண்டையும் பார்த்து ஸ்க்ரூட்டினி பண்ணதுக்கு அப்புறமா சிலபஸ்ல இருக்கா இல்ல சிலபஸ் விட்டு வெளியில எடுத்திருக்காங்க அப்படின்னு பாக்குறது இவங்க பார்த்துப்பாங்க. அத வேணா இம்பார்ட்டன்ட்.
Can you hear me please?
ஒரு யூனிட்டுக்கு 15 கொஸ்டின் கண்டிப்பா அவன் படிக்க மாட்டான் அப்படின்னு சொன்னாரு சார்.
Can you please hear me?
You are audible, but some audience has some.
Yes, please ask them to switch off the microphones because I cannot.
Participant name Nirmala Devi, please mute yourself. Majid ji, please mute the audience.
I think as organizer you can mute the microphone.
Dr. Nirmala, please mute.
பார்ட் B ல ஒரு யூனிட்டுக்கு ஒரு क्वेश्चन தான் வருது அப்படினா 3 क्वेश्चन கொடுக்கலாம். பார்ட் B ல 2 வருது அப்படினா 4 கொடுக்கலாம். அந்த 4ஐயும் நம்மளால எழுதி வாங்க முடியும். 3 யூனிட்டுக்கு எழுதி
only host can mute her actually.
Yes, the host can mute the microphone.
Out of 5 2 ஆக்கணும். Out of 5 2 10 4 ஆக்கணும். இல்ல மேம் ஸ்க்ரூட்டிங் பண்றது இவங்களா இருக்கலாம். இவங்களும் ஒரு क्वेश्चन எடுத்துப்பாங்க. இன்டர்னல் ஒன்னு எடுப்பாங்க, எக்ஸ்டர்னல்.
Professor Majid,
collect to please.
Sir, we are doing just
okay.
Yeah, it's done. Professor Adela, really sorry.
Now, please.
Really sorry.
Can you hear me, please?
Yes, you are audible.
Okay, thank you. So, as I already mentioned, it was a theorem proved by Chen that x of t, a rectifying curve, can be written in this shape, where y is a unit speed curve. This was one way to construct rectifying curve. Also, I mentioned that the centroid of a unit speed curve is also a rectifying curve. So this was another way to construct rectifying curves. And if we consider the dilated centroid, we can also construct a rectifying curve. By our result, we introduced the new methods for constructing rectifying curves, more precisely as evolutes of spherical twist curves. So we started from the very simple example of a spherical helix Y, which has this parametrization, cosine t, cosine at plus 1 over a sine t, sine at, and so on. So this is a spherical helix. We computed the unit vectors of the frame of the curve, and also the curvature k tilde and the torsion tau tilde. And we found these very simple expressions. If we denote by S the arc length parameter of Y, then S has this expression, and then ds over dt is square root a square minus 1 cosine t. To construct the evolute, we use the formula we mentioned before. So we need to calculate first the primitive of the torsion, which we denote it by capital T. It's very simple to calculate. So the primitive of the torsion is the simple linear function t plus c. And then we introduce them in the formula. And we obtain that this is a family of rectifying curves, which has very nice shape. Minus sine c sine at over a cosine t plus c, sine c cosine at over a cosine t plus c, and minus sine c square root a cosine t plus c. So we constructed rectifying curve by using our method. And we remark that any rectifying curve defined by this formula can be also written as a dilation of a unit speed circle on the sphere. And moreover, if we denote sine c, capital C equals small c here, then we've got that x of t equals c secant t plus c zt, which is in accordance with the result of Bang-Chen, where zeta is this unit speed circle. We also note that all the rectifying curves defined by our family of rectifying curves lie on the cone. That cone has this equation, and moreover, they are geodesics on this cone. I mentioned at the beginning of the talk that at the end, I'll come back to this result. And we draw a figure. In the next figure, we represent the spherical helix Y defined by 59, this one. And now let me go back to the, okay, for A equals 6 and for different values for capital C. We took 2, 2.2 and 2.4. So we have a spherical curve, and we constructed from the spherical curve a spherical helix and three of its evolutes, and they are rectifying curves. So we just, in a few minutes, I'll end my talk. So this was published as an invited paper in mathematics in the special issue Differential Geometry Theory and Applications, Part 2. This is the paper published together with my colleagues. And we've got a nice surprise because the next published paper in the same special issue was also on rectifying curves, more precisely on the geometrical properties of the light rectifying curves and the centroids. And also probably because the paper was published at the end of 2021, and we imagined that our figure looks as a Christmas tree ornament, probably. I don't know. This is our explanation, is a joke, of course. So we are very glad to see that the paper from which I presented the results was the cover story of the mathematics journal for December. So here are the references, but I already wrote them in full in the talk. And let me just end with few words. We know all that geometry arose as a field of knowledge dealing with special relationship. And geometry was one of the two fields of pre-modern mathematics, the other being the study of numbers, so arithmetic. And classical geometry was focused in compass and straight edge constructions. And of course, the geometry was revolutioned, sorry for my English, by Euclid, who introduced mathematical rigor and the axiomatic method still in use today. And his book, The Elements, is the most famous. And in modern times, geometric concepts have been generalized to a high level of abstractions and complexity, and have been subject to the methods of calculus and abstract algebra, so that many modern branches of the field are barely recognizable as the descendants of early geometry. I'd like to mention here that my co-authors are not geometers. So my co-authors on this in this paper are working in algebra and mathematical analysis. But we have tried to find a common subject. So I think this geometrical presentation of the cars was also very nice for them. And in fact, we try to go back to the beautiful geometry of curves. I did not work too much on geometry of curves, as you said, I mainly work in some manifold theory, and I am very glad, and I say hello to all my friends and co-authors which I met in this conference. They presented very, very nice talks on some manifolds, but at this time I chose to talk something more geometrically, and I choose a topic on curves in Euclidean space. So thank you very much for your invitation, and I hope to see you soon again, also face to face. And again, I say hello to all my friends in this meeting. Thank you to the organizer. Thank you.
Thank you, Professor Adela. Really, it was very nice lecture on rectifying curves, and not for the young researchers, but for UG and PG students also. Really, it was very wonderful lecture. So, is there any question or comment from the audience?
Can I have a question?
Yeah, sir, please.
Yeah. Thank you very much, Adela, for your nice talk. Just small remark only. You mentioned that is is a cotangent of the primitive of for the evolute. Just to see it, just you wrote the tangent. I think normally is cotangent. What evolute? Expression of the evolute, just to mention like that. If you see the slides, just so, this is.
You want me to see a slide, yes, Mohammed?
Yes. About the evolute, just
okay,
because.
Just a moment. I was looking for the meeting because I could not see you. Okay, just a moment. Okay. Where?
For the evolute, the definition of the evolute, yes. Just down when you wrote that is down. I mean, later. I said, you give the primitive tangent. Here.
Yes.
This
Yes.
is T. It is. I think it's cotangent, not tangent. For the book, is cotangent. Primitive of the torsion.
I know the book of Shaum, and is but there is converse.
Is written cotangent. Anyway, it's okay, but it's okay. Just remark. Another thing.
I'm not sure it's cotangent. I think it's tangent. We calculate again, Mohammed.
Anyway, in the book is cotangent, and it just very simple remark.
Okay.
Yeah. Thanks a lot for that.
This is the book I use. I don't know if you
I
can
have
see.
it. We have it. We have it. I know it. Yeah, we have it. I have to compare. Thank you.
Okay.
It's very nice.
As you know, I did not work too much on the geometry of curves, but because my colleagues are not geometers, that we try to find something
very nice.
And this was a very short project. Was only for 4 months. And in 4 months, we wrote the project and we also published the paper. So it was like a hey-roop.
No, for the result, it's very nice description. Very nice description. Thank you very much.
Thank you. Nice to see you.
Thank you.
Thank you very much, Professor Adela. Thank you very much, Professor Mohammed Bel Khalifa. And on behalf of organizing committee, I again make a thank to you.
Hello.
Now, our next, Professor Afsoos Ali Sheikh. He wants to say something.
Yeah, I am Professor Afsoos Ali Sheikh. Professor Adela Mihai, congratulations for the nice talk. But I have some queries. Hello, Professor Adela Mihai. Am I audible to you? I have some queries. The first one, in which software you have draw the last figure? In which software?
In MATLAB.
MATLAB. Okay.
Yes.
Okay. Very good. There is a nice picture. And do you know?
Yes.
Who have studied this variety of rectifying curves, oscillating curves, normal curves in a surface under surface isometry? That are very recent papers from 2019 to 22.
Yes.
A series of papers in good SCI journals. I will give you the list of my papers. Recently, I have done with my collaborator, Dr. Pinaki Ghosh. You can see there are 7 papers. I am sending you the list published from Journal of Geometry Physics, Indian Journal of Pure and Applied
Mathematics. Thank you so much.
Okay.
Let me write in the chat here. I can write my email address. So if you can please send me on this address.
Sure. And please convey my regards to Professor Mihai. He knows me.
Yeah.
Okay.
Thank you so much. He has classes just now, so he could not attend the talk. Yesterday he was in this conference as well, but thank you.
Thank you very much for a nice talk.
Thank you, Professor Shaikh. Thank you. I just wrote my email address, so if you can please send me some references.
Just now I will send you.
Thank you so much. Thank you. It was very nice to see you all and very nice to meet you.
Okay, thank you very much, Professor Adela. Now, next speaker is Professor Sirajuddin. Are you there, sir? Professor Sirajuddin?
Yes, can you hear me?
Yeah.
Okay.
So before we start with Professor Sirajuddin, let me briefly introduce him. Professor Sirajuddin is currently in...
Introduction has been done yesterday. No need to introduce me.
Okay, sir. Professor Sirajuddin is from King Abdulaziz University, Saudi Arabia. Currently, he is professor there. And yesterday, due to some technical glitch, we were not able to listen to him. So today, we have fixed his lecture now. So it's your session now, sir. It's over to you.
Okay. Majid Bhai, can you tell me how to? Last time I add the file, multiple participants can share the simultaneously. So I choose this option to share the file. I think is one participant can share at a time. This option. So
okay, either you can send it to me directly. You can make.
Oh, okay, okay, no problem. No, I think I can. Let me share. Okay, can send to you by email.
Yeah.
Okay, just give me 1 minute. So you can send. Yes, so wait here, I'm sending you. Please check your email.
Yeah. You sent it, sir?
Yes, I sent. I have sent. Your Yahoo mail.
Yeah.
Check please.
Yeah, but it's
Click inbox, then you will find.
Yeah, I received. I received. But this one is empty, sir.
Yes.
It is empty, sir.
Empty? No, it's not empty. Just wait. It's empty. Okay, let me see. Let me share here. Share the screen. Multiple participants. Okay. Share the. Okay. You can see now.
Yes.
Yeah, it is visible.
But wait, it is visible. Okay, let me. Here. Okay. Sorry, by mistake. So the first page, is it?
Yeah.
Okay. Good afternoon, everyone, and thank you, Dr. Adela, Professor Adela Mihai, for nice talk. I didn't ask the question. Maybe I will ask later because I don't have much knowledge about the rectifying. My question was that if the point belong to the, we will discuss inshallah later. Okay. So the title of my talk is the recent development on silencer manifold and some applications on related to the above product. So because silencer manifolds have a lot of applications, so we cannot cover in this talk. I give just a little, and silencer manifold of the different structure also, almost solution, and basically initiated by Professor Bang and Chen for almost complex manifold, and then later on is extended to the almost contact and locally product Riemannian manifold. So here I have taken the locally Riemannian product and it's their applications. So geometry of silencer manifold initiated by Professor Bang and Chen, and these are the generalization of holomorphic and totally real submanifold. Before silencer manifold, only holomorphic and totally real and CR submanifold is studied. So in 1990, Professor Bang and Chen introduced the idea of silencer manifold. It has many applications, and these idea extended to in contact geometry by Lota and Cabrillo and their collaborator, his collaborator. In case of locally Riemannian product manifold, Professor Bayram Sahin and Mehmet Echkin studied slant and bicylinder submanifold in locally product Riemannian product manifold. Then to extend that idea of slant, if the submanifold is not slant, so what is that actually? If not slant, if the slant, the definition, the function is not depend on the point, neither on the vector field. But if there is a slant, but it's neither depend on, it is depend on the point. If we change the point, the theta has been changed. So what is that actually? So this new idea is given by Fernandez Tayo in I think it's around 1999, and he called them quasi-slant submanifold. So that actually that idea is point wise, is depend on the point. So that because Chen introduced recently in 2012, Chen and Ozegare introduced the point wise. So here we also define the point wise submanifold. That idea extended for the other structures also, and have a lot of applications. So I'm giving here some applications. Professors Beng and Chen introduced the VAP product in submanifold actually. Before it was in 1969, O'Neill and R.L. Bishop, they have given the idea of VAP product, even before also. But on the submanifold theory, it was not defined. So Professor Beng and Chen studied CR VAP product. Later on, geometry dedicator Professor Sahin proved that if one factor in place of totally real, if we choose the slant factor, fiber or base of the VAP product, so whether the VAP product exists or not. So he found that there is no VAP product in semi-slant exists in Kähler. And same thing happened in contact also. But in case of Kenmitsu manifold, yes, are you there? Can you hear me? I think something is.
Yeah, you are audible.
Okay, yes. So later on, you see in Kenmitsu case, such VAP product exists, and we have done with Professor Mihai and Adela Mihai that in Kenmitsu case, it is just when taking one of the factor is slant. It has many applications. The one direction is existence and uniqueness. People are here, they have done the existence and uniqueness theorem for slant submanifold, and itself the existence and uniqueness theorem also have some applications, so I'm not going to that. And select helix also. Chen-Rishi inequality. So recently with my student Abdul Qadir, we did the Chen-Rishi inequality for VAP product also even. And Professor Adela Mihai and some many researchers studied Chen-Rishi inequality for the general submanifold. We did for VAP product also. And applications to VAP products such as semi-slant, hemi-slant, and sequential. In all these three cases, or maybe so is QCR VAP product or generic VAP product. So that one factor be considered as a semi-slant, is slant, or if it is a generic, we can consider as point-wise slant. So that it has a lot of applications. Now here I'm giving some basic. So this tensor field F is said to be almost product structure if F square equal to I and F is different from plus minus I, and the Riemannian matrix satisfying like Kähler. So this is the almost product Riemannian manifold definitions, and then it becomes locally Riemannian product if F is parallel here. The Gauss and Van Garden formula is given here. So these are the we need in calculations. This is the relation between the shape operator and the second fundamental form. Submanifold is said to be totally umbilical if the second fundamental form can be written in terms of the mean curvature, and is totally geodesic if H is 0, and minimal if mean curvature vector is 0. And the relation between the square norm of the second fundamental form is like this. We define here this. And if we have choose a vector, X is tangent to the submanifold, then F is on the ambient manifold of the locally Riemannian product. So it can be decomposed into tangential and normal component. T is the 1-1 tensor on M, and omega is the normal valued one form. Similarly, if we have a normal vector on the normal bundles, can be decomposed tangential and normal. So if f is 0 here, in this case, f is 0, no, tx is 0, then fx is equal to omega x, so totally real, and omega is 0, so fx is equal to dx. So in and actually we call it here invariant and anti-invariant. Okay, Celant submanifold. So we give the definitions like chain here in locally Riemannian product. The submanifold is said to be slant if for each non-zero vector x tangent to n, the angle between the tangent space and the fx is here actually the f is the 1-1 tensor. The angle is constant. It's neither depend on the point or neither is on the vector field. So if theta is slant immersion, then m is called the theta is called the slant angle of the slant immersions. Invariant and anti-invariant are the special case of slant submanifold. If theta is 0, then invariant, theta is pi by 2, then slant, totally anti-invariant. This result, Professor Sahin proved in Korean Mathematical Society, and he proved that a submanifold is said to be slant if and only if t square equal to lambda I. Lambda is equal to cos square theta. So the eigenvalues lies between 0 and 1 of t square. And this idea has taken from contact and in contact and locally product Riemannian manifold. Original idea is given by in Chain book and his paper in Slant Immersion Bulletin of Australian Math Society in 1990. This is a consequence of this lemma of this theorem. So this is also we can use here for the slant part. And we give here some examples of slant submanifold. So here you see if we have a structure, so f of del upon del xi is equal to del upon del xi, and f of del upon del xi is minus time. So this is a locally Riemannian product. Even though minus 1 on the first and second plus, or both are plus, so it will be locally Riemannian product. Yeah. We have a example here. Since suppose the two-dimensional submanifold in R4. So this is the slant with slant angle 2 theta. Another example is also on the two-dimensional. So this is a slant. And here is, so we have seen here that in example 1 and 2 and 3, both cases are the even dimensional slant submanifold. And here in example, this example, also even dimensional. So this is okay. But here, this example, the slant submanifold is odd dimensional. So in case of complex manifold, here is the geometry is different. That's why it is interesting. In case of complex manifold, the slant submanifold is always even. But here, in this case, slant submanifold, maybe even, maybe odd, not a problem. So in locally Riemannian product. So here is odd dimensional, 3-dimensional submanifold. So here I have mentioned the remark that in example 1 to 4, the slant submanifold are even, and example 5, the slant submanifold is odd dimensional. So we can see that in locally Riemannian product manifold, the slant submanifold may be even or odd. Semi-invariant, one distribution is, there are 2 orthogonal distributions, D and D per, that TM decomposes D direction D per. D is holomorphic, invariant, and D per is anti-invariant with respect to F. And submanifold is said to be semi-slant. So one distribution is slant here and one is holomorphic. So semi-slant submanifold are the generalization of CR and slant, as well as invariant and anti-invariant. Hemi-slant, one factor is one distribution is slant, another is totally real. So in case of point-wise, if d theta is a point-wise slant distributions, we will give the examples of point-wise also here. So if the d theta is point-wise slant, then point-wise semi-slant and point-wise hemi-slant. We are giving here the example of R4, R2 cross R2. The vector is given here. It's two-dimensional, so this is an example of hemi-slant. One is d theta is spanned by E1 and d theta is d perm is spanned by E2. And so one holomorphic, another is slant. Sorry, one is anti-invariant, another is slant, so it's hemi-slant. Our aim is to using that the slant factor in warp product, so that's why I have to define here warp product.
Relations
1969, R.L. Bishop and B. O'Neill introduced the idea of warp product, and they defined the manifold on the matrix G of xy is G1 xy plus f square G2 xy. And here you can see, because some people are not familiar, so they can see the warp product, the massive star and black holes. We cannot see, but you can see the surface of revelation, the product between the curve and the circle. So we can, let me check whether we can draw the picture here or not. I think it's not. So yani surface of revelation is one of the example of warp product. The distance is from the center to the circle is not constant. Cylinder is an example of product manifold. So because the line and the circle. So function is constant in that case. So if the function become constant, then it is called Riemannian product. He has given in his book or in his paper, one of the paper, he proved that M is equal to M1 and M2, two product Riemannian manifold, Riemannian or semi-Riemannian, even pseudo-Riemannian manifold. Then M is a warp product. If M is a warp product, actually, if M is a warp product, then nebula XY is in TM, that is, yani, M1 is totally geodesic. And here nebula XZ, X is in M1 and TM1 and Z is in TM2. So this can be written as X lane FZ. And nebula is the connection on the ambient, on this M. And nebula dash is the connection on M2. So nebula ZW, if the both vectors are from the fiber, the first one is called the base and the second one is fiber. Yes, so nebula ZW is equal to nebula dash ZW minus G of ZW gradient lane F. This formula this lemma actually play a very important role when you are doing warp product. In the beginning of this century, Professor Beng and Chen initiated the idea of warp product manifold, and then many papers published on warp products. And some applications are also given. So it is clear from that proposition here that M1 is totally geodesic and M2 is totally umbilical in M. Actually, we are studying here by taking the one of the factor is slant. So we start from the CR. Sorry, we start from the semi-slant. One is invariant submanifold and other is slant. And there are two possibilities, MT product FM theta and M theta product FMT. So we will see here, if MT product FM theta, then there is no warp product. He proved in Mathangarica in 2019, and he said the function is constant. I skip the proof here. So then he reversed the factors, that the base he consider the base is slant and the fiber is anti-invariant. So he proved that the such warp product exists and has given many some examples also. So, and he proved the characterization by using the very well-known theorem in HIPCO, that there are two orthogonal distributions on a Riemannian manifold. Suppose D1 and D2 both are involutive, and D1 is totally geodesic foliation and D2 is a spherical foliation. Then M is a locally isometric to a warp product. He used this theorem and he proved that M is a semi-slant submanifold of the semi-slant submanifold. And semi-slant submanifold becomes warp product. Then M is locally product Riemannian manifold of the form M theta FMT, where M theta is proper slant and M theta is invariant submanifold. So in the same paper we proved this. If this is some relation A omega U y is equal to A omega U F y equal to minus sine square theta. U mu is actually in F y. U is in d theta and y is in d per d. D actually here for the simplicity, the tangent space of the TM, TMT, any MT. So tangent space of MT we denoted by D. This is actually not a distributions; they are integrable. And tangent space of M theta we denoted by D theta, like that. They are not distributions. With Farley, Salami, and me, we proved the inequality also for this case. And we have given some examples. We prove in Hajitepe Journal of Math. So we proved that if this is a proper warp product semi-slant manifold, and then the square norm of the second fundamental form satisfies this inequality, where gradient theta ln f is the gradient of the function ln f along m theta, and the equality hold if and we prove the one side actually. Equality hold, and then mt is totally umbilical, and equality hold, then the this is totally geodesic in m tilde, not in m, and mt is totally umbilical. This is m theta is totally geodesic, mt is totally umbilical in m tilde. And furthermore, this is a mixed totally geodesic. Mixed means if we choose a one vector from m theta and another, so second fundamental form is 0. That's a mixed. So we have given here some examples. This is two-dimensional. So two-dimensional submanifold of R4, and this is warp product actually. The invariant is from V2 and anti-invariant is from V1. And you calculate this metric. So this is actually this is cos square theta and sine square theta, and this 2, 1, and 1. So this 2 actually. Yeah, 4 du square plus u square d theta. So this u is a function actually, warping function. So the metric of d theta is here. D theta metric is u. Here 4 du square and u square d theta square. So this is the warp product metric in the form. Another example we consider in 4-dimensional. So we have given here, and the idea is we can see that the distribution D is spanned by Z3 and Z4. Okay, here this is D, and D theta is spanned by Z1 and Z2 with the slant angle cos inverse 1/5. And you can see the metric is also here is this is 1, 2, 3, and 4, 5. 5 D and du. No. This is here X and S and T. So here is okay. Yes. This is Z3 and Z4, Z1 and Z2. So we can find 1, 2, 3, and 4, and 5. 5 du square plus ds square, and s square times d theta square plus d phi square, like that. So we have given that, like these examples in our paper. Now the next possibility is that we replace invariant submanifold by totally real. So there are also two possibility, m perv and fm theta. We will check whether it is working or not, m theta and fm perv. So this is first we need to define the hemicylind submanifold. So hemicylind, one is holomorphic, another is totally real. We defined before also. And see here, the hemicylind are two type, m theta and n perv, and m perv and n theta. So Mehmet Eshkin in Bulletin of Australian Math Society, he studied and proved that if we choose the first factor is totally real, anti-invariant, and this m theta is slant, so there do not exist such warp product. Then other case with my student, we have done that the other case exists, and we give the characterization by using the theorem and inequality also. This chain actually has given the inequality for CR warp product. So on the basis of that, so also this is really interesting. Is another generalization. If we are choosing m theta is suppose holomorphic, then it becomes CR. So it is the generalization, but it is mixed totally geodesic. Then if you put theta is 0 here, so this is infinity, going to infinity, but mixed, because of mixed, this happened because of mixed totally geodesic. If it is not mixed totally geodesic, then it will be, you have to consider actually. We have given the examples also here on that paper. So submanifold given by the equivalent this. So here is also, this is a hemicylind of this form, and this is 6 du square plus 2u square dv. So this is gm theta and gm perv. So this is the metric. Yes, what happened actually in case of semi-cylind, point-wise actually, where we have to define the point-wise. See, in that previous paper here, if you look here, this is here. What happened if this m theta is point-wise, not cylind? Whether such warp product exists or still not exist. So this case, in case of semi-cylind, if mt and m theta, sign prove that this is do not exist for cylind. But if m theta is point-wise, then what happened? So we proved actually in geometry and physics that such warp product exists, and we have given brother. Actually, I have a talk in the seminars, so maybe I will continue after that. Okay. It will, yeah, today inshallah we will do that. Okay, no problem. So I'm sorry, my student was calling me. Actually, he has a lecture. Oh, okay. So this is the case that when if we are choosing this, so this is the slightly change. You know, m theta is point-wise, so it's changed completely. So here we are actually. Yes. This point-wise, before defining the point-wise warp products, semi-cylind or hemicylind, we have to define the point-wise cylind and point-wise. A submanifold of locally Riemannian product is called point-wise if each point P in M, the Wittinger angle theta between fx and tm is independent of the choice of non-zero vector, but it is depend on the point. Okay, so we choose non-zero vector. So theta is a function actually. We note that the point-wise cylind submanifold of locally Riemannian product manifold is called slant in the sense of chain. You know, this is point-wise becomes slant if theta is globally constant. So if the function is constant, then point-wise becomes slant. So that means slant is point-wise. What converts is not true. On a similar line of chain, yes, we have to define, we have to give this result for point wise also, like a slant. T square equal to minus cos square theta p. Actually, we put here point p. Otherwise, look like a slant I. So this is theta is actually theta p, so that we can understand. And also we can see that b omega x equal to sine square theta and c omega x equal to minus omega tx. This is easy relation. By using the structure equation and this above relation, we can calculate it. As we have seen in the previous section, there are two possibilities. In hemicylind, Mehmet Echkin proved that such Waugh product do not exist in Bulletin of Australian. But and in case of cylinder, in case of semi-cylind, Behram-Sahin proved that if m theta and mt, so mt and m theta also do not exist. So there are two possibilities that we have to consider that the m theta is pointwise. So here we have seen that if we consider m theta is pointwise, so such Waugh product exists, and we have given the example here. Suppose we are considering the two-dimensional submanifold of R6, and here is this is the metric. The first one is so I, because of the no space, so I didn't mention which one is. I skip the steps that d perm and d theta is spanned by what. But here you see d theta is here is a pointwise slant submanifold. Yes, pointwise hemicylind m perm and fm theta. This one is holomorphic, sorry, totally real, another is slant, and the function is not a constant. Let me share the file that maybe later I will share the whole things what we have done there. So this short I have given you here, and here also you see this is the example. I also cannot come, so I make it tiny here. This x1 is equal to u cos hv, x2 equal to u sin hv, minus v u sin hv, u cos hv, and the square root 2b, x1, x2, x3. This 6-dimensional. So we consider two-dimensional submanifold in R6. So we have seen that one is holomorphic, sorry, and anti-invariant, and other is, and also both, because this distribution is spanned by a single vector, so they are integrable. So we have an integral manifold corresponding to the integral distribution, integrable distributions, because the vector is spanned by the single vector. There are two vectors and is spanned by one with d and d perm, and another is d theta. So they are integrable by definition. So they are integrable. So integral manifold. So corresponding to the integral manifold is m perm and m theta. So we can write the metric is in this form, and you have seen here. This is 2 cos hu 2v whole square and gm per this. This is actually doubly Waugh product. The function is on both sides. V here and here also u square. So this is actually doubly Waugh product. We prove the characterization using that. So proof we skip here because of short time. So here m is a pointwise hemicylind submanifold. Any one of the factor is pointwise. If it is cylind, then such Waugh product do not exist. This do not exist if it is cylind. But if it is pointwise, then exist. And we have given the examples before. We have some example more, but here I have just given two. M is a locally Waugh product submanifold of the form m per product fm theta, if and only if this hold. And we prove the inequality also here. So this is the Waugh product pointwise semi-cylind submanifold, then such inequality. And these inequality generalized CR case also. If theta is globally constant, not constant, if theta is 0 actually, so this becomes a CR case. So theta put 0 here. So this is P gradient cleanup. So this result generalized a professor's sign published in Bulletin of Romanian Math. So, and here are some references which we have given. We did this actually YWA product also with Professor Mihai, and see some example. If I just consider here the related references, a lot of work has been done on WA product, so we just consider the related one. Professor Bang and Chen, we published here in Publication Math Everything, and here also in Revista Argentina, and there are some others. So here we have given actually a lot of work of Professor Mihai and some others, but we didn't give here because we just concentrate only the locally Riemannian product. So we just give the papers of locally Riemannian product. Yes. See this locally Riemannian product, and with very recently Professor Bang Chen and Mihai and me, we did, and it will come soon, that we proved that there is no point-wise semi-slant in Sasakian. So it will be appear inshallah in the next volume of Rexam. Yes, so this we did here point-wise semi-slant. The case which I have not mentioned here, the case is geometry and physics, and we did here with Professor Adela. It's the locally Riemannian product of YWA product and so on. Thank you for your attention.
Thank you very much, sir.
Majid
really
bhai,
nice
I cannot hear the voice a little because there is a problem in the mic. Please speak loudly.
Yeah. Thank you very much, sir. Really, it was very nice lecture, and you actually collected results, and you started the slant submanifolds, and nowadays every geometer is often using slant, semi-slant, or hemi-slant submanifolds. So your collection is really nice. It was really nice lecture. We have one question in the chat box. It is
one question about what?
It is as E1 contains trigonometric functions, why E2 is without trigonometric functions. I think he's talking about frame field. Tahir, are you there? Tahir Manzoor has posted this question. You can see in the
chat. Give me 1
box.
minute. Let me bring the mic from the colleagues. Okay, just give me 1 minute, please.
Okay.
Sorry, he is not here. Yes, I can hear you. Please tell me. You are talking about the trigonometric function involved in that.
Yeah.
It's not necessary that, let me share the file actually, the original file. That's in that file we have given in detail. Okay, just give me 1 minute. So share, how can we share? It is, just wait, let me see, it is. Just wait, I just share the new file, yes. Yes, here we are. Yes. You can see the file. Brother Majid, can you share the file? Can you see the file?
Yeah, sir. It's visible.
Okay. Yes, we have given the example. You said about the point wise. So let me go to the point wise here. You see, suppose here we are. So see this. No, this is constant angle is here constant. This is here. So this you see variable are u and v. So theta is constant. So it's, theta is constant. So this is slant. And if you are looking here, so this is also constant. Here you go. This is also constant. Okay. Some examples I have given here. Let's see. This is point wise actually. Yes. See this theta and phi, two variable.
Yeah.
Okay. We choose theta and phi, and the immersion is defined in R6. So Z1 and Z2 are here. So we can see the angle here, theta, suppose theta 1, we choose the angle. So it is 2 phi, and 2 phi is variable actually, phi is variable. So the angle depend on the function, is it? On the variable.
Yeah.
So that's why this is point wise. In the previous examples we have shown there, so that is, so this is point wise. See this another example. We are considering the u and v vector, and here the d perm and d theta is spanned by z2, and the angle is cos 2v over 3. So yani angle is depend on v. Here v, is it?
Yeah.
Yeah. So this is the idea, and see here also the angle is depend on u. So we have given 3-dimensional also and 2-dimensional. So it is easy to construct the example. Here you see the distribution is depend on d theta, and it is the angle involved here u.
Yeah.
Is it u and w? So it depend, the angle is depend on the variable.
So
here, yeah. So this.
So I think Dr. Tahir has got his answer. It was a question from Dr. Tahir. So I think he has got the answer. Is there any other comment?
Majid bhai, I have to ask something.
Yeah.
Do you have any other question, please?
Someone was saying.
Yeah, Majid bhai.
Yeah. Ramshankar Gupta sir is there.
Yes.
Dr. Ramshankar.
Yeah, I want to thanks Professor Siraj for nice survey on the slant sum manifold of warp product manifold.
Yes, sir. Thank you so much.
I have just one query, sir. Like
Yes,
you have
sir.
mentioned so many examples here.
Yes,
and
sir.
the product manifold which you have taken in examples, they are basically Euclidean spaces like R2. R2.
Yeah, we have taken the non-Euclidean is for difficult for me to calculate. Construct the exam.
So,
yes.
I mean, I'm just curious about it. Is it possible to consider the product manifold like sphere, like S2 cross R2 or something?
Yeah,
and
you
then
see,
we can look for some
let's see, in case of CR, for example, look S6, for example. So in case of S6, the CR warp product exists, but not semi-slant.
Okay.
So I have seen, I've been there in Belgium.
Okay.
So, these Professor Mirjana and his collaborator in Belgium, Professor Mirjana is from, Serbia. She's from Serbia. So they are doing, really, it was very interesting. I have seen that they give the example in S6. But in my opinion, you can see that the semi-slant in S6 do not exist.
Okay.
Because, you see, the S6, the dimension cannot be more than 6 of the submanifold. So suppose you consider the holomorphic is 2-dimensional, because it's in case of almost complex manifold, it is always even. So minimum 2-dimension of the invariant, yani holomorphic. And slant is also even dimensional, so 2-dimensional. So the submanifold dimension minimum will be 4 in case of Wapro. Now going to the normal bundle. So you have their FD theta direct sum mu. So FD theta is dimension is 2. So mu is 0 actually in that case. So yani it will be completely immersed in S6. This is the things actually. In CR is okay.
Okay, so means you are saying like
But
semi-slant also not
maybe in higher dimensional, we can think over that.
Okay. Okay, thank you, sir. Thank you.
Yes. Any other question, please?
Hello. Hello.
Yes.
Professor Shiraj, how are you? This is Professor Abdul.
Yes, fine, sir. How are you?
I'm fine.
Yes, sir.
Congratulations for the nice talk.
Thank you, sir.
You did a lot of things in this theory of submanifolds, semi,
Yes,
heavy, etc.
Yes.
So you are the experts in this area. I don't know
Yes, sir.
whether is it possible to extend these kinds of results or ideas in the W word product or twisted word
Yes,
product?
of course. We can, you see, I have given one example. W product. Have you seen that example? I have. Let me see. It is. Sorry, it was here. I think in case of yeah, you see, this is the example I have given. See, the function is V involved here on the first metric also, and here is also involved.
Yes.
So that means what
W
this becomes W. So is it possible? You know, we can think over that. Yes. And that generalize, single warp product. W can generalize single.
So I think this can be applied to this physics also.
Yes, yes. Many applications, now, yes, yani warp product doing something related to the cosmology also. Professor Beng Yin Chen initiated the things. Yes. Professor Adela Mihai, do you have any comments, please? Are you there? She is not here, I think. Any? Zafar, sir?
Yes. Assalamu alaikum. How are you?
Assalamu alaikum, sir.
Maalaikum salam. क्या हाल है भाई?
He is my ideal teacher. Yes, sir. Alhamdulillah, sir. आप कैसे?
It was a very nice lecture.
Thank you, sir.
You covered a lot of things. Very nice.
Yeah.
Congratulations.
Thank you so much. Professor Rakesh, you want to? Yes.
Namaskar.
You are doing.
Namaskar, sir.
Namaskar. How are you?
Very fine, sir. आप कैसे हैं, सर? आप?
अल्हम्दुलिल्लाह. आप कैसे
आपका
हैं?
बहुत अच्छा था लेक्चर, और क्योंकि स्लाट पे हमने भी बहुत काम किया है, तो हम बड़ा
जी
अच्छा लगा।
जी, मैं नाम नहीं ले पाया। I'm so sorry for that. जी
नहीं, मैं इस लहजे से नहीं बोला था, मैं तो जैसे ही बोला।
नहीं, मैंने देखा आपका काम जी, और वो हमारे ये उसमें जो हिमाचल में है वो भी अच्छा काम कर रहे हैं, टीम उनकी भी है, आपकी टीम है, और इधर हमारे बंगाल में तो माशाल्लाह अच्छा काम करते हैं लोग जी।
और जफर सर
थोड़ा सा मैं भी आप लोगों से सीखने की कोशिश करता हूँ, कुछ कर ऐसी हाथ पैर मार के। जी, आप कैसे हैं? जी,
हम तो आपसे ही सीखते हैं सर, और जफर सर की बात आप कर रहे हैं, जफर सर तो हमारी भी आइडल हैं सर
जी।
जफर सर से तो हमें बचपन से सीखने को मिल रहा है।
They are our motivation, you know.
जी, एग्जैक्टली हाँ जी। नमस्कार सर, जफर सर।
नमस्कार। वहां बिठा दो, ऊपर कुतुब मीनार पे बिठा दो।
नहीं सर, नहीं,
कि फिर उतरना भी मुश्किल हो जाए।
नहीं सर, ये देखिए रिटायरमेंट के बाद बंदा एक्टिव कहाँ रहता है, आप बताइए। माशाल्लाह आप हर जगह एक्टिव रहते हैं, ये बहुत बड़ी बात है। दिस इज अ वेरी, मतलब मैं आपके बारे में क्या कह सकता हूँ, आपकी शान में कुछ कहा नहीं जा सकता, ये तो बड़ी बात है इसमें।
ठीक है, सबके चाय और खाने ड्यू हो रहे हैं, आ जाएं।
नहीं सर, ये आप हमारे लिए भी दुआ करें कि हम लोग रिटायरमेंट के बाद
भाई और सिराज भाई सही कह रहे हैं सर।
जी सर, यस सर।
चलने जी, मोहब्बत है इन लोगों की, ऐसी कोई बात।
थैंक यू सर, थैंक यू वेरी मच।
सब मोहब्बत।
प्रोफेसर मोहम्मद आकिफ, माशाल्लाह And Professor Welkifle, I'm really very thankful to you. I have listened your talk, and Professor Zafar Saab. I was busy here in the class. Yes, sir.
Professor Siraj,
Yes,
congratulations for
Thank
your
you so
nice
much.
talk.
Thank you.
Actually, I will start to learn Indian.
Yes, sir.
Thank you. I am listening. I am listening to you, but
Yes,
I couldn't understand anything.
Really?
Let me learn. I have many friends. You know, I have many friends from your country, so
Yes,
I am very happy that I have known you. So thanks again for your nice talk.
Thank you, sir.
In the future, maybe I can also try to write some papers related to warped product or different areas. Thank you.
Yes,
Thank you so much.
Okay, sir. Thank you.
So thank you very much, one and all, who contributed in any way in this session. A special thank goes to Professor Rakesh Kumar, the first lecturer who delivered the talk from 2 to 2:40. Then Professor Adela Mihai, and the third was from Sirajuddin. All of them delivered a wonderful talk, and I'm very much thankful to them on behalf of organizing committee. Now our session C will start, and this session will be chaired by Dr. Rakesh Kumar, and the contributory talks will be given by Dr. Agazin Bahadir, Dr. Musawwir, and Dr. Sabina Asmin. So Dr. Rakesh is already there, sir.
So thank you, Dr. Majid.
Yeah, over to you,
for
sir.
giving me this opportunity. So I think the first lecture is by Professor Bahadir. Professor Bahadir, are you available?
Yes.
Dr. Bahadir, are you listening to me? Am I audible?
Hello.
Hey, hello. Hello, sir.
Hello. How are you?
Very fine, sir. Very fine. So actually, the problem is we are late by more than 30 minutes. So it is my humble request to you, please compile your results within 10 minutes. Please excuse me for that.
Yes. No problem.
So let me introduce Professor Bahadir to all the participants. Dr. Bahadir is from Department of Mathematics, Faculty of Science and Letters from Turkey. He is in KS Imam University. So he has done his MSc PhD from the same university, and I know him from the last 2 years, and he wrote 4 papers, such paper, he wrote around 20 research papers in very good research journals, and he presented more than 10 research papers in various national and international conferences. He visited to various foreign countries like Kosovo, other countries. So without wasting much time, so I hand over to Dr. Bahadir. So please share your PPT and start your talk, sir, please.
Thanks.
Ben ateistim dedi, eline omuzuma koydum, maşallah ne kadar güzel dedim.
Professor Siraj sir.
Yes.
Please stop your sharing, sir. Now Professor Bahadir, please share your PPT, sir.
Yes.
Sure. It is visible to all of us.
Yes. Hello. I would like to start my presentation by first thanking the organizing committee. In this study, we will give a new definition about golden and metallic structures. So far, we have had 2 studies produced using these definitions. One of them was printed. A member of metallic means family, the golden mean has been used in many ancient cultures as the basis of proportion to compose music, design sculptures and paintings, or build temples, palaces. It is assumed that some members of metallic means family, particularly the golden mean, silver mean, information geometry is a method of exploring of the world of information by means of modern geometry. Concept of information have so far been studied using mostly algebraic, logical, analytical, and probabilistic methods. Because geometry examines the mutual relations between elements such as distance and curvature, it should provide powerful tools to information science. Information geometry has appeared from studies of invariant geometric structures involved in statistical inference. It presents a Riemannian metric together with dually coupled FN connections in a manifold of probability distributions. These are important structures not only in statistical inference, but also in the broader fields of information science, such as machine learning, signal processing, optimization, and even neuroscience. Amari introduced the concept of statistical manifolds via information geometry. Statistical manifolds are endowed with a dual connection and another conjugate connection in affine geometry. Takano defined a new type statistical manifolds, which including almost complex, almost contact structure. Takano introduced generalized almost complex and almost contact statistical manifolds, calling them Kehler-like statistical manifold and Sasaki-like statistical manifold. Inspired by this study, we introduced golden-like and metallic-like statistical manifolds, which are a generalized version of golden manifolds and metallic manifolds, respectively. This study also includes examples of these structures. Basic concepts. Definition polynomial structure as follows. Equation 1. If polynomial structure satisfies Q phi equals phi squared plus I, then phi is an almost complex structure. If Q phi equals phi squared minus I, then phi is an almost product structure. If Q phi equals phi squared minus phi minus I, then phi is an golden structure. If Q phi equals phi squared minus PQ minus QI, then phi is an metallic structure, where P and Q are two integers. Definition, this definition, golden semi-Riemannian manifold or semi-Riemann or a golden Riemannian manifold is called. Let Mg be a semi-Riemannian manifold and let phi be a 1-1 tensor field on M, satisfying the following equation. Then the tensor field phi is called a golden structure on M. If the Riemannian metric G is phi compatible, then triple Mg phi is called a golden semi-Riemannian manifold or Riemannian manifold. The Riemannian metric G is called phi compatible if satisfies equation 3 for any xy in gamma Tm. Let G be phi compatible and phi be metallic structure on Riemannian manifold M, then Mg is called a metallic Riemannian manifold. Using the equation 2, we have these relations. It's note that by putting P equals Q equals 1 in above equations, metallic structure reduced to a golden structure. Members of metallic family are classified as follows, where kappa PQ represent the family of metallic numbers in where golden structure, silver structure, bronze structure, silver structure, copper structure, nickel structure. Definition: let phi be a metallic structure on M and let nabla be a linear connection on M. Then nabla is called a phi connection if nabla phi equals 0. Metallic Riemannian manifold Mg phi is called a locally metallic Riemannian manifold if the Levi connection nabla of G is a phi connection. A remarkable fact about golden structures is its appearance in pairs. If phi is golden structure, then phi hat equals I minus phi is also golden structure, but same is the case with almost tangent and almost complex structure. So it is natural to ask the connection between golden and product structures. Let M be a semi-Riemannian manifold. Denote a torsion-free affine connection by nabla. The triple M nabla G is called a Stassen manifold if nabla G is symmetric. We define another affine connection nabla asterisk by the equation 3 for a vector fields x, y, and z on M. The affine connection nabla asterisk is called conjugate or dual to nabla with respect to G metric. The affine connection nabla asterisk is torsion free. Nabla asterisk G is symmetric and satisfies this equation. Actually, this Levi-Civita connection nabla 0. It is clear that the triple M nabla asterisk G is statistical. Some papers with relation Takano's paper, some papers, pinching theorems for statistical submanifolds in Sasaki-like statistical space form. These others, some inequalities for statistical submanifold of quaternion Kahler-like statistical space. Generalized normalist Casorati curvature for statistical submanifolds in quaternion Kahler-like statistical space form. Chain inequalities for statistical submanifold of Kahler-like statistical manifolds. Statistical manifolds with almost quaternion structures and quaternionic Kahler-like statistical submersions. Our main definition. One. Sorry. Let Mg phi be a golden semi-Riemannian manifold endowed with a tensor field phi asterisk of type 1 satisfying the equation 4. Equation 4 vector fix x and y. In view of 4, easily derive equation 5 and 6. 5 and 6. Then Mg phi is called golden-like Stassen manifold. According to equation 5 and 6, the tensor field phi plus phi asterisk and phi minus phi asterisk are symmetric and skew-symmetric with respect to G. The equation 4, 5, and 6 imply the following proposition: Mg phi is golden-like Stassen manifold if and only if so is Mg phi asterisk. Example. Consider the semi-Euclidean space R1, 2 with standard coordinates x1, x2, x3, and the semi-Riemannian metric G with the signature minus plus plus. Let phi be an 1-1 tensor field on R13 defined by as follows for any vector field where P is a golden mean. Then we easily obtain phi squared equals phi plus I. This implies that phi is golden structure. This is standard golden structure. Now we define an 1-1 tensor field, different tensor field, phi asterisk on R13 by as follows. We can easily see that this equation. Also, we have equation 6 also. Hence, R13G phi is a golden like Stassel manifold. Another example, generalized version of above example. Let Rn be a 2n plus m dimensional F space with the coordinate system.
Bahadir, sorry for interruption. Can I ask you please go to your main important results? Can you skip your examples? Actually, we are shortage of time actually.
Okay.
I am highly excused for that.
Okay.
Thank you.
Example, first example, generalized example about golden like Stassel manifolds. This relation, we define phi tensor field as follows. Then phi is golden structure on Rn 2n plus m. Moreover, if the conjugate tensor field phi asterisk is defined as follows, then we can easily that Rn 2n plus mg phi and this triple are golden like Stassel manifolds. Our new main definition too. This similar golden like Stassel manifold in where we define a metallic like Stassel manifold, similar golden like Stassel manifold. Let mg phi be a locally metallic semi-Riemann manifold and with a tensor field phi asterisk as follows. In view of 7 equation, we easily derive equation 8 and 9. Then mg phi is called metallic like Stassel manifold. Similarly, we give a proposition. We remark that if we choose phi equals phi asterisk in a metallic like Stassel manifold, then we have a metallic semi-Riemannian manifold. Example, consider the Euclidean space with coordinates. If we choose phi as follows, in where kappa is equals metallic means, metallic numbers, then we obtain phi squared equals p phi plus qi. Moreover, we can easily see that standard metric on our 6 is phi compatible. Hence, this structure is a metallic Riemannian manifold. Another example. Consider the semi-Euclidean space R13 as follows. Metric signature as follows. If we define tensor field phi for this. In where kappa metallic means members of metallic means family, then we obtain phi squared equals p phi plus qi. We can easily that also metallic structures, this phi metallic structures on R1 tree. Now we define new tensor field phi asterisk, the relation of this equation. Thus we have this equation. Moreover, we have the equation 7. Hence, this triple is a metallic-like system manifold. Generalized version above example as follows: G metric phi tensor field, where kappa members of metallic means family, Rn 2n plus m bn 2n plus m-dimensional F space with the coordinate system. Then phi is metallic structure. Moreover, if the conjugate tensor field phi asterisk is defined as, then we can easily that these triples structures are consist metallic-like statistical manifolds. Thank you so much. Our references. Using this definition, we have published a paper. Also, it is published. Also another paper accepted Journal of Open Mathematics. Thank you so much for listening.
Thank you so much, Professor Bahadur, for very informative and nice talk. Because time is short, so I request the participants, if they have any questions, then please contact Bahadur directly. So thank you, Dr. Bahadur, again for your such a nice talk. So
thank
Dr. Musawwir, Musawwir bhai, are you available?
Yes, I'm here.
Okay, thank you, sir. Thank you. So, are you ready, sir?
Of course, I'm always.
Okay, so let me introduce our next speaker, Dr. Musawwir Ali from Department of Mathematics, Aligarh Muslim University. So he did his PhD from Aligarh Muslim University under the guidance of Professor Jafar Hassan, and he has lots of awards and grants in his credit, like Best Paper Presentation, Young Relativist, and many others. He also delivered many talks in various national and international conferences, workshops, and symposiums. He has around 30 papers in his credit, and he has visited so many countries. So without wasting much time, so I welcome Dr. Musawwir Ali to present his talk. And I also request to Musawwir Ali, because we have shortage of time, if it is possible for you, so kindly go to your main results, please, if it is possible for you.
Actually, you see that I was given 20 minutes and then 15 and now 10 minutes, and now the main results I have to show.
So thank you.
So this is actually the way in the society too, that the people who are really contributors are marginalized. Okay, no problem. Actually, because the time is very short, so I will focus. Very rare things that is not given by different speakers till now. Okay, please ask Dr. Bahadur to stop his slides, please.
Dr. Bahadur, please stop your sharing the PPT. Dr. Bahadur.
Yes.
Please stop your sharing the PPT, so that other speaker can also share his PPT.
Yes.
Musawwir, assalamu alaikum.
Who is this? Yes.
Danish.
Oh, Danish. Okay, nice platform. It is actually to saying hello, hi, and from long time, Danish and Siraj bhai were not in contact.
Okay.
Thank you. Yes. Oh, it's not stop, Dr. Bahadur.
It is still available, sir. Still available. Dear Danish, how are you?
How are you, Dr. Rakesh? How are you? I'm fine.
Very fine, sir. How are you, sir?
कैसे हैं सर आप?
जी बढ़िया सर. आप खैरियत सर?
जी सर सब बढ़िया है सर. ठीक है.
मुसव्विर भाई आप कर लीजिए प्लीज.
Okay, is this visible on the screen? Yes.
Yes, it is visible, sir. Visible, sir. Yes.
Okay, so this is actually the topic of my talk is eta resultants analysis in LP Kenmesu manifold and space-time of general theory of relativity. So as I am directed that I have to present just a few main results. So, and this is, this is not, this is my first attempt to study this eta resultants, and this is the combined work of me and Dr. Abdul Hasif. So this is first time I am using eta resultants in my my area of interest, that is general theory of relativity. So I will not explain much about the Ricci flow and the Ricci resultants, as in first day lecture, Professor Zafar Hassan explained very well and very deeply the concept of Ricci resultant and Ricci flows, and all the work that we have done earlier in my related to the Ricci solitons and symmetries of space-time. He has explained very well, so I am not going to explain again and again. And Professor Afsoz Ali Sheikh also given the talk, nice talk on the subject. So I will just explain few points, key points on this topic, related basic background that is not explained till now. So, okay. So introduction, preliminaries. So I will just use very related definitions to reach there at the main results. And this major section that we have done in our research paper, I will skip and just I will cite. That's why I named it as cite and skip. Okay. So, okay, abstract of the talk is simple. I will discuss basics and the backgrounds of the Ricci solitons, a brief introduction of the previous work that already Professor Hassan has given. So I will skip that part also. But I will focus here on the recent work on eta Ricci solitons in LP Kenmesu manifolds and space-time of general relativity. So this will be the my main object of the talk. You see that Ricci flow, you know already that this equation is a partial differential equations, which is showing the Ricci flow, and Ricci flow is already coined by Hamilton before 40 years. But you see that Ricci flow is very important because its importance lies in the solving the Poincaré's conjecture. And there were lots of attempt has been made earlier, but this is actually the concept of Ricci soliton that make it possible to solve the that conjecture, very important conjecture. So I will give few minutes here. Okay, so you see that this word Ricci flow, you see Ricci flow, if you okay, if you see this picture, you can say this kind of picture is showing the process of the Ricci flow. And somebody asked in Professor Hassan's lecture that is there any video on this topic. Yes, of course, there is a video by James Isner, Ricci flow video. It's a very nice video. You can see by clicking this link. Okay, so why this Ricci flow is important, I will just write few lines that Hamilton's call it as evolution equation, and evolution equation because it is actually evolving the Riemannian metric G with time by its Ricci curvature tensor. That's why it is called as the evolution equation. And to attempt the attempt of solving the Poincaré's conjecture, Hamilton thought it as a second ordered partial differential equation, which was parabolic, quasi-linear, and equally homogeneous, equally or homogeneously in all directions of the flow. So this word is very, very important when we are using such kind of concept in general theory of relativity. The elliptic version of this equation is actually the case of Ricci flat. So its version, elliptic version, is for Ricci flat. It is very much used in Ricci flat space-times. And the hyperbolic version is actually of our use. I mean, the people who work in the Lorentzian space-time or Lorentzian manifolds, they use such kind of equation, Ricci flow equation, for the hyperbolic case of the Ricci flow equation. Okay, so it is called as the diffusion equation. Hamilton himself is called it as diffusion equation, and Professor Essen very well explained why it is called as diffusion equation. He had also given an example of the differential equation, which was the diffusion equation, and that governed by the Ricci flow, okay, and Ricci-Soliton. Now Ricci-Soliton, 1 minute I will take on this topic. Soliton is another thing. Sorry, Ricci is combined with the Soliton. Ricci-Soliton was explained by Hamilton in 1982, but before a century ago in 2 centuries ago in 1834, the word was coined. It had the dictionary meaning, and the dictionary meaning in this year was exactly same that is used by Hamilton in 1982. And what was the dictionary meaning and from where it was coined? I will show you that Scott Russell was a geographist, you can say. He wrote a paper, wave of translation, in which he coined and he developed a modeling of shallow water waves. And water waves are actually governed by the diffusion equation. So the Soliton wave was coming from here, and the same paper was showing that self-similar solution of Ricci flow was called as Soliton. Why self-similar solution? Actually, he find that when there is a translation of the waves, the shapes of the wave are preserved under some transformation, and he find such kind of solution, called it as Soliton. Okay. Self-similar solution and fixed point solution term was coined from here. And then we study the symmetries of Ricci flow, and we find that these symmetries are scalings and diffeomorphism. So this is actually, these are very important terms whenever we are discussing the Ricci flow and its fixed point solution, that is Ricci-Soliton. Okay, that is Ricci-Soliton. So you see that this equation actually has great importance due to the solution of the point conjecture problem, that every closed simply connected 3 manifold is a 3 sphere. Okay, and an Einstein metric is a special case of the Ricci-Soliton. Okay, this triplet, metric, vector field, and this constant on a manifold, I mean this triplet on a manifold M with a Riemannian metric G and vector field U, satisfying this equation, or in local coordinates we write this equation as this, then this equation shows the equation of Ricci-Soliton. I mean, solutions of these equations are actually the Ricci-Solitons. Okay. Okay. The next term is eta Ricci-Soliton. This is my first attempt to study the eta Ricci-Soliton, because Dr. Hasib has done a lots of work on Kenmatsu manifold, and he asked me, the eta Ricci-Soliton and solitons are having great importance in theory of relativity. And this is directly, I find that it is directly showing the symmetries of space-time in Einstein spaces. So I try to find the relation or association with eta resultants and symmetries of space-time, and that we obtained. Actually, we obtained many results on these eta resultants when we associated the LP Kenmetsu manifold with the Lorentzian signature, and we reduce the dimension of the space, or suppose the dimension of the space as 4, and we choose the pseudo case also, and then we find that this is very much compatible with the space-time of general relativity. And very I mean old results also we have reduced in the case of general theory of relativity. And you see this equation giving, the Ricci-Soleton is, this part is the Ricci-Soleton, and this additional term give you the generalization of that old concept Ricci-Soleton as eta Ricci-Soleton. So there is lots of work done by Kao and Kimura, and Kalin and Krasmarianu also has done on some work on the eta Ricci-Solitons. Okay. These are the preliminaries. I will not explain. There are lots of preliminaries we have used for the development of this research work. Okay, so this is structure phi xi eta g be admitted by a differentiable manifold and of dimension n. Then it is called as Lorentzian almost paracontact metric manifold. So this definition I'm not exploring much, but Lorentzian almost paracontact metric manifold with certain condition is known as the LP para Kenmetsu manifold. I have written here the paracontact structure will be called as K paracontact structure if xi, the vector field, I have taken the definition as Killing vector. And now this is the main definition that I have used in my research, that we call a Lorentzian almost paracontact manifold M as Lorentzian para Kenmetsu manifold. Okay, K LP Kenmetsu manifold, provided this condition holds. Okay, so this definition I will be using in main result. So I am skipping all these things. So there are certain preliminaries. Okay, and this is one more definition I may use there. An LP Kenmetsu manifold M is called an eta Einstein manifold if its Ricci tensor AS is expressed as this, and θ1, θ2 are smooth functions. In particular, if θ2 equal to 0, the M is named as Einstein manifold. This is actually the generalization of Einstein space, Einstein manifold. Okay, and this is you can say nowadays it is our favorite tool that we work on the Weil conformal tensor, and the expression in LP Kenmetsu manifold we have written here in this equation 2.20, and this equation will also be used in main results. Okay, so an LP, okay, I'm skipping this lemma also. You can see the young researchers or the people who are interested to work in eta Ricci-Soltons and LP Kenmetsu manifold, they can see these results and calculation. That's why I have named it as cite and skip, because I know कि time आखिर में कम रह जाएगा मेरे पास. So this is the work we have done. This is important. The Pandey and his collaborators in this reference I have given, you see they have developed a theorem or proved a theorem, and that theorem is I use this theorem, okay, in my result, that if the structure, this structure be admitted by n-dimensional LP Kenmetsu manifold M, then M behaves like an eta Einstein manifold. Okay, this M has constant curvature given by this equation. The scalars lambda and rho are related by this equation, and in particular, if rho equal to 0, we get lambda this. So I use this slide in my research work. Okay, I am coming on the direct. I am watching expression of Dr. Rakesh. Okay, so this is actually main section of my research. You can say of my talk. So this definition, the conformal curvature tensor is said to be conharmonic if the divergence of the tensor is 0. So in equation 2.20, I have given the expression of the this conformal curvature tensor, and when this property holds good, it is called as harmonic. Okay, this is the vector V is called as conformal vector field. Okay, you see this is one kind of symmetry property, and symmetry properties of the space-time already shown by Professor Zafar Hassan. So I'm not explaining it. It is simply the Lie derivative proportional to the metric tensor. Lie derivative metric tensor is proportional to the metric tensor, so it's a conformal symmetry some kind. Okay. Okay. So this is the result. However, the proof is given before the result, that let M be an n-dimensional LP Canmesu manifold admitting G, Xi, lambda, rho. I mean, this is structure. Okay. Then the manifold is of conharmonic curvature tensor if and only if the manifold is an Einstein manifold. Also, the Ricci soliton on M is always shrinking. Why it is shrinking? Because you see okay. You see R, no, not R. Okay, lambda is constant. That is because n is greater than 2, so lambda is negative. And you see that the Ricci soliton depends. I mean, the kinds of Ricci solitons are defined, are given in terms of that constant lambda. If lambda is positive, then expanding. If lambda is negative, then shrinking. If lambda is 0, then it is steady. And also, if lambda is some gradient of some function, it is called as gradient Ricci soliton. And if the space is Einstein space, then it is called as the soliton is called as the trivial soliton. So these are the kinds. So if in this case the lambda is negative, so we say that in this case the Ricci soliton on the manifold or Canmesu manifold is always shrinking. Okay, this is the equation. You know that equation. This is Einstein field equation. And in general, I mean in local coordinates and in general coordinates, these are given like this, or you can write it okay, TIJ, I mean energy momentum tensor in terms of metric tensor, whenever these equations 4.6 and 4.7 and 4.8 by virtue of 4.6 and 4.7 takes this form. I mean, from this equation we can come here if we are using 4.6 and 4.7. Okay, 4.6 and 4.7, we get this 4.9 equation. Okay, now the Lie derivative, because the symmetry I am studying, so Lie derivative of the energy momentum tensor is now given in terms of the Lie derivative of metric tensor. Now it is very I mean important to see that the symmetry related to the metric tensor is now the symmetry related to the energy momentum tensor, but in some special cases. So we have if I use it as Killing vector, so on the right hand side it is 0, because for Killing vector Lie derivative metric tensor vanishes, so this is 0 and Lie derivative energy momentum tensor becomes 0. So we have a result that if an n-dimensional LP Canmesu manifold together with this structure satisfying Einstein field equation without cosmological term, then the Lie derivative of energy momentum tensor vanishes along the vector field Xi if and only if Xi is Killing. So you see that very easily we are I mean obtaining the results in for eta Ricci solitons also. Okay, important thing is just you make the two spaces compatible, and the structure there should be compatible in the I mean space time of general theory of relativity. Okay, so this is the conformal symmetry, you know that, and we can use from equation 4.10 we can write it as, and we can write this equation as this, and we write this equation. Okay, it is very simple from that relation. So this is symmetry inheritance property. General definition of the symmetry inheritance property is this. and this is in 4.14 satisfied for the energy momentum tensor. So we can write the result. In LP, n-dimensional LP Canvas manifold with structure this and satisfying Einstein field equation with cosmological constant, the energy momentum tensor has the symmetry inheritance property if and only if vector field is conformally killing. And always, whenever you are using conformal killing vector, and always you can have a consequence or corollary by taking, that vector as killing vector. So direct result give you the direct consequence also. Okay, this is another result, so I am skipping it. Okay. Okay, the energy momentum tensor in perfect fluid in the form we can write. You know the energy momentum tensor for perfect fluid. Okay, sigma stands for the energy density and rho is isotropic pressure. Okay. Ax is non-zero one form, and this relation we know. F is unit time-like vector. By the equation 4.6, 4.7, 4.16, this equation, that 4.6 which was showing the Lie derivative of energy momentum tensor, okay, will leads to this equation. And if you replace the two vector fields as one equal xi, so this equation reduces to, okay, by using this 2.1 and 2.5, and we get 4.19. And finally, from this relation, whenever we are using equation 4.18, 4.19, we get this. This is very important equation 4.20. And you know that equation is what? So we have a result that G xi lambda rho be an eta Ricci-Salton in an n-dimensional Canvas space-time of harmonic conformal curvature tensor. If the manifold satisfy Einstein field equation without cosmological constant, then the matter contains satisfy the vacuum-like equation of the state. For dust in perfect fluid, this equation holds good. Okay, from equation 4.20, 4.21, it follows that P equal to 0. So again, we have a result. This eta Ricci-Salton in an LP Canvas space-time of harmonic conformal curvature tensor. Then the manifold admitting dust for perfect fluid is filled with the radiation. Okay, Dr. Rakesh, I will just show my slide. I have studied psychology also, so I can understand your facial expression.
Thank you, sir.
Thank you, sir. Okay, these are the reference. अगर किसी को मेरा कुछ काम देखना है तो मैं आपको पर्सनली शो कर सकता हूँ. Okay, these are the references. Me, my student, and my guide, we have worked on this subject. And actually, for me to deliver a talk in front of Professor SN is really not easy task. मैं बैठा हूं तब भी मेरी टांगें कांपती हैं.
I know, sir. I know.
Okay, so these are the references.
Thank you, Dr. Musawir, for such a nice
talk.
Thank
you very much.
And I know because you have compiled so many results in a one talk, so I expect that most of the participants have many questions to ask from you. So I request all the participants, if they have any questions, please contact Dr. Musawir directly, because we have some shortage of time. So thank you, Dr. Musawir, again for such a nice talk. And I also congratulate Professor Jafar Hassan for having such a nice and good student, I say. So thank you again. So the next participant is
may I say something, Rakesh? May I say something?
Yes, sir. Sure, sir. Sure.
Such students are my assets.
Yeah.
And they are fulfilling my dream. My dream was how to put together the geometry and relativity people
together. Yeah.
So they are fulfilling my dream. I'm very happy now.
Yes,
thank you very much.
Sir.
Congratulations. Go ahead. Thank you.
Thank you, sir. Thank you very much. Thank you very much for your blessing always, sir. So next speaker is Dr. Sabina. Are you available?
Yes, I am present here.
Please, yeah, thank you very much. Dr. Musawir Ali, please, can you stop your PPT, sharing your PPT? Yeah, Dr. Sabina, please share your PPT. Let me introduce in few minutes, few lines. Dr. Sabina is from Department of Mathematics, Chandidas Mahavidyalaya, Brindam, West Bengal. So I request Dr. Sabina to please share your PPT and start your lecture. And I also request to you, if it is possible, please go through the main results and please compile your lecture within 10 or 15 minutes. At the most 15, within 10 minutes, if it is possible, then it will be better.
Okay, sir.
Please continue.
Okay, sir. Am I audible?
Yeah, you are audible, and your PPT is also visible to us.
Okay, thank you.
Thank you.
Good afternoon, everybody. First of all, I would like to thank the organizers of the conference, especially Dr. Majid Choudhury, for giving me the opportunity to present my paper. I am Dr. Sabina Yasmin, Assistant Professor of Chandidas Mahavidyalaya under the University of Burdwan, West Bengal. The title of my paper is Curvature Properties of Morris-Thorne Wormhole Metric. This is the joint paper with D. Chakraborty and M. Sarkar. Introduction. Einstein and Rosen, in reference 28, proposed the existence of bridge through space-time, which connects two different points in space-time and thus theoretically makes shortcuts that can reduce travel time and distance. This shortcut is known as Einstein-Rosen bridge. In this paper, Wheeler reinterpreted the Einstein-Rosen bridge as a connection between two distinct places in space-time with no mutual interaction and introduced the notion of wormhole in 1962. Morris and Thorne, in reference 50, presented the most simple metric in 1988. This metric serves as a wormhole that can theoretically be traversed by human beings. It arrives as an exact solution of Einstein field equation with a cosmological constant. Morris and Thorne presented the most simple metric in equation 1, where t is the global time, L is the proper radial coordinate, d is the same constant, and c is the speed of light. A space-time is a connected four-dimensional Lorentzian manifold. The curvature determines the shape of a semi-Riemannian manifold, and the curvature of a space-time is determined by the metric of the space-time. If we impose the restriction on a curvature tensor of a manifold by means of covariant derivatives of first order or higher orders, then it produces a geometric structure known as curvature-restricted geometric structure. Such structure plays a crucial role to explore the geometry of a semi-Riemannian manifold. For example, symmetry of a manifold is defined locally by the restriction del r equal to 0, and semi-symmetry of a manifold is determined by the curvature condition r dot r equal to 0. Also, the recurrent classes of manifolds and pseudo-symmetric manifolds in the sense of these are respectively the generalization of locally symmetric manifold and semi-symmetric manifold. Such geometric structures carry important intrinsic geometric meanings in reference 37 to 39. In general relativity, there are many space-time metrics which are relevant and significant physically. The physical structure or what is of such metrics are well studied due to the information of a specific cosmological model. But such metrics might have carried several geometric information which are yet to know. In this context, we mentioned that Sek and his co-authors first initiated the study of geometric structure of various significant space-time in the following references. Curvature restricted geometric structure. For two symmetric 0 to tensor A and D, their Kulkarni-Inoue product A and OSD is defined by the 0,4 type tensor field given as follows. In terms of Kulkarni-Inoue product, the 0,4 type conformal curvature tensor C, the circular curvature tensor W, the conharmonic curvature tensor K, and the projective curvature tensor P can be written as follows, where R, S, and K are the respectively the Riemann curvature, Ricci curvature, and scalar curvature. Let it be a 0k, k greater than equal to 1 tensor field by operating the endomorphism EXY and XY with respect to A on F. The 0k plus 2 tensor E dot F and QF known as Tachibana tensor are defined respectively as follows. Here are the definitions. A semi-Riemann manifold is said to be pseudo-symmetric in the sense of this if the tensor R dot R linearly dependent with the Tachibana tensor, that is R dot R equal to LR where LR is some smooth function. And next definition is pseudo-symmetry while conformal tensor. And this definition If the tensor R dot R is linearly dependent with QSR, that is the condition, this is called the Ricci generalized pseudo-symmetric manifold. The next definition for scalar alpha and 0 less than equal to k less than equal to n minus 1. Let on a manifold M, the rank of the tensor S minus alpha G is k, then M is called K quasi-Einstein manifold. And for k equal to 1, it is quasi-Einstein manifold, and k equal to 0, it is Einstein manifold. A Ricci simple manifold is a quasi-Einstein manifold for alpha equal to 0. This is the definition of generalized rotor type manifold. So next definition, an Einstein manifold of level 4, respectively 3 and 2, is defined by the this equation, respectively this and that on M, where lambda I less than equal 1 less than equal to I less than equal to 9 are some scalars. The Ricci tensor of manifold M is cyclic parallel if this relation hold on M, and Cauchy decision tensor is defined by this relation. Let E mu is the endomorphism corresponding to a symmetric 0-2 tensor mu. Then for a 0-4 tensor field E, mu is said to be E compatible if this equal to 0. Holds on M. Again, if phi tensor product phi is E compatible, then the one form phi is said to be E compatible. So for a 0-4 tensor field E, the curvature two forms. Omega MEL are recurrent if and only if this hold, where S is a cyclic sum over y1, y2, y3. Also for a 0-2 tensor field mu, the one forms lambda mu L are the recurrent if this relation hold for some one form. So next definition, if we consider this relation, let the solution set of such equation constitute a vector space LM. If dimension LM greater than equal to 1, then M is called E space by Vinci. Let us consider geometric structure of Morrison spacetime. Let us consider the space R4 equipped with the Morrison matrix G, which in terms of spherical coordinates TLV phi is given by the equation 3. By using a program developed by Professor A.S.A. in old firm Mathematica, we have calculated various components of different curvature tensor and their first order and second order covariant derivatives. I must acknowledge Professor A.S.A. and his groups working in the Department of Mathematics, the University of Burdwan, for their help and cooperation during the preparation of this paper. The non-vanishing components R and S are written as follows. The scalar curvature is given by this. And these are the components. Thus, based on this data, we can state the following theorem. The Morrison wormhole metric has the following curvature properties. It is really simple as S equal to alpha eta tensor product eta holds for alpha equal to 2b square by b square plus r square, eta equal to 0, 1, 0, 0 with eta norm eta equal to 1, and hence it is special quasi-Einstein. It has a special Ricci generalized pseudosymmetry as r dot r equal to QSR satisfied. C dot C equal to this, that is the metric is equipped with the pseudosymmetry while conformal curvature. It satisfies the condition K dot K equal to 0, that is semi-symmetric due to the conharmonic tensor. Conformal curvature two forms are recurrent for the one form. This it is neither rotor type nor generalized rotor type, but the tensor G with S and G with S2 S squared are linearly dependent by this relation. It is Einstein manifold of level 2 as it fulfills S square equal to this. The Ricci tensor is compatible for the curvature C, R, W, P, and K. Energy momentum tensor of Morrison metric. In Einstein field equation, the energy momentum tensor T of a space-time is presented as TAB equal to 1 by tau G, capital GAB plus lambda small GAB, where capital GAB equal to this is called Einstein tensor, lambda is the called cosmological constant, and tau equal to 8.
Excuse me, Dr. Sabina.
Yes.
Sorry to interrupt you. Please, can you go to your main result, please? By skipping the introduction and this general part.
C4, this is the non-vanishing components are given as follows, and thus we can state the following theorem. The energy momentum tensor T of the Morrison wormhole metric admits the following geometric structure. 1 and 2, and the energy momentum tensor T is compatible for the curvature CRW, P and K. Gödel metric and Morrison metric. Gödel in 1949 proposed a model of the universe which is filled with the incoherent matter and allows the closed time-like curves. The Gödel metric is given by equation 4, where A is a non-zero real constant related to the angular velocity measured from any non-rotating dust grains. The curvature properties of Gödel metric were studied by Seg, Days, Hotlos, Jelowski, and Kundu. Since both Gödel and Morrison spacetime raise the theoretical possibility of time travel, we would like to note the similarities of their geometric properties in terms of curvature, which are given as follows. Number one, both are simple manifolds. They are of special decisionalized pseudosymmetry. Both are Einstein manifolds of level 2. Both of them are manifold of pseudosymmetry while conformal curvature. Conformal two forms of both the space times are recurrent. Their recitential are compatible for CRW, P and K. These are the references. Thank you so much.
Thank you, Dr. Sabina, for such a good talk. But the problem is that the time was very short. So again, thanks to you. So I request the participant, if they have any questions, they please contact her directly so that you can get your answer. So now I hand over the mic stage to Dr. Majid. Please, Dr. Majid.
Yeah, yes, sir. Thank you very much, sir. And I must thank all the speakers for their kind cooperations. Actually, we are a very, shortage of time is here, so we are already late. So now I directly hand over to Professor Khwaja Moinuddin Saab. He will chair the next session. Khwaja sir. Khwaja sir.
Thank you, Dr. Majid.
Over to you, sir.
Thank you very much. A very good evening to all. This is Dr. Khwaja Moinuddin from Department of Mathematics, Manu. This is going to be the last session on contributory talks. After this, we have a brief valedictory section. I welcome you all for this section. This session has 4 talks as per the schedule. The first one is by Dr. Fasih Ramandi. Next one is Dr. Muhammad Aqib. Third one by Dr. Anu Devgan. And the last one by Dr. Abdul Malik Muhammad. Earlier, we were planned that each talk will go for 15 minutes, but keeping the time constraint into consideration, I request all of you that finish your talk within 10 minutes. Okay. Dr. Fasih Ramandi's brief is available here.
Yes, I'm here. Okay. Good evening.
A brief introduction of Fasih Ramandi. Dr. Fasih Ramandi did his PhD from Amir Kabir University of Technology, Tehran in the year 2016. He is mainly working on the applications of differential geometry in theoretical physics. He has to his credit more than 20 research articles of international repute. He is working as an assistant professor for Imam Khomeini International University, Iran. The title of the presentation of Dr. Fasih Ramandi is Affine Metric Geometry and its Application to Relativity. I request Fasih to deliver his talk, and I request him to please finish the talk within 10 minutes. Fasih, over to you. Start.
Yes. Okay.
Thank you.
Good evening. Thank you so much that you invited me to this symposium. The title of my presentation is about gravity and dark matter in the framework of metric affine geometry. In this paper, we generalize a space-time manifold by considering a affine metric structure on a space-time manifold. Affine geometry is defined in terms of 2 independent structures, the Riemannian metric and the general affine connection. With the help of the metric structure for contraction of Riemannian curvature of the affine connection, we formed a natural density for gravity and matter. Using calculus of variations, we derived 2 field equations. The first one retrieves Einstein field equations, and the other equation describes matter in space-time. In this framework, the affine connection is related to concept that is well known as dark matter. So we can interpret the dark matter as a factor which leads curving and twirling the space-time. According to general relativity, space-time is a four-dimensional Lorentzian manifold with the Levi-Civita connection of the metric G. Metric tensor is responsible for calculating the distance, while affine connection handles the straightness and twirling the underlying manifold. These two geometric structures are fundamentally independent variables and play different roles in dynamic of space-time. This fact motivates us to an alternative approach to the standard theory of general relativity named metric affine gravity. Since Levi-Civita connection is uniquely determined by the metric, so and the geometry that describes gravity is purely metric geometry, and in this work we have used metric affine theory of gravity, which is called Platini formalism. As I mentioned before, in this work, we shall consider a metric affine geometry in which the connection and the metric tensor are fundamentally different variables. In this framework, we retrieve Einstein's field equations, and we will show that the concept of dark matter is directly related to affine part of the connection. Metric affine geometry begins with the definition of an affine metric connection. The space of all affine connections on a manifold M is an affine space with this space as its underlying vector field. So any arbitrary affine connection on M can be written as the following form. In this paper, we consider the case in which we have A equal to alpha x y minus alpha y x, where alpha is one form on M. By considering this connection, we can compute by direct computations that the Riemannian curvature of nabla overline nabla is the following form. Have the following form. Because we have metric tensor, we can using metric tensor to contraction this Riemannian curvature tensor of affine connection, and we can obtain this notion Ricci of x of and y is equal to this equation. Again, by using metric tensor for contraction this Ricci tensor, we can find a scalar curvature for nabla, overline nabla. Okay, let me say again, because I am not smooth in English, if I have if I have used the wrong structure, please forgive me. I am not smooth in English. In this work, we consider this comment. Okay, we use this connection. And we compute Riemannian curvature related to this connection. Then, with the help of existed metric structure, we contracting Riemannian curvature to obtain Ricci and scalar curvature. Now we can use this structure in relativity. So, okay. And the critical point of Einstein-Hilbert functional, known as Einstein matrix. By using this idea, we define a new Hilbert-Einstein functional for metric affine manifolds as follows, where R is the scalar curvature of our affine connection. Let me show here. I have considered that. Excuse me. I have considered alpha to be df for a smooth function f. Okay. In this work, for application to relativity, I have considered alpha to be df differential of a smooth function on M, and using calculus of variation, I have obtained two new equations. These equations. The first of these equations is the Einstein field equation, and the last one is related to the notion of matter. Tracing both sides of this, the first equation yields R equal to -3 df squared. It is well known that the scalar curvature R is related to matter distribution in space-time of the space-time manifold. Hence, F is related to matter distribution in space-time. But df has a fundamental law of affine connection which is responsible to curving a space-time. So dark matter can be geometrically interpreted as curving and twirling of a space-time manifold. Suppose that nabla F is time-like, then according to equation 3.5, nabla F can be interpreted as a current of some mass which satisfies the conservation law. If we find T df equal to 3/2 df squared g minus 3 df O times df, which is the right hand of equation 3.4, we can see the divergence of this tensor is vanished, which reminds us the conversation of stress energy tensor. And finally, we we present an example of metric affine space-time, which is similar to Schwarzschild space-time. Let m equal to n times 0 to infinity in this manifold with this metric g and this function f. We see that f, m, g, and f satisfy our obtained equations. And as
Dr. Fasi, sorry to interrupt you. Please try to conclude in 2-3 minutes, please.
Okay.
Thank you.
As t approaches to 0 in this model, universe become smaller and density of matter increases to infinity. Time t equal to 0 is not in our space-time, and this is time, and this time is the instant of Big Bang. And here is our references. Here our references we have used. Thank you for your attention. Thank you very much for your attention. Okay. Thank you very much.
Okay.
It is my first time that.
Any questions from the audience? The session is open. If any questions are there, it's okay. Otherwise, we will proceed to the next presentation.
I want to thank you everyone and say I am so sorry I'm not smooth in English, and it is my first time that I'm talking in English and in online, in virtual space.
So you are most welcome. It's okay. Nicely presented. Thanks a lot.
Thank you. Thank you very much.
Now I will call the next presenter.
Thank you, Professor Fasi.
Dr. Muhammad Aqib.
Thank you, Mr. Danish.
Dr. Muhammad Aqib did his BSc, MSc, and PhD from Jamia Millia Islamia, New Delhi. He is having around 20 publications to his credit. Many book chapters are written by him, and in total, he is having around 5 years of teaching experience. I request Muhammad Aqib to deliver his talk. Muhammad Aqib.
Good evening. Am I audible?
Yes, yes. Good evening.
Thank you. Thank you so much for providing me an opportunity to present my work, some pinching result for warp product slant submanifold in nuclear metallic product space form. Before starting the presentation, I would like to acknowledge this is my joint work with Professor Ubaidin Bahadur and Dr. Muhammad Aslam. Though my presentation is divided into the 4 sections, but due to the time restriction, I will skip some part of this presentation. Actually, the first part of the presentation is warp product, a brief introduction. Second, metallic Riemannian manifold. Third, curvature invariant. And last one is some application of the result I have obtained. So in the first 2 sections, I'm actually just focusing why someone will be interested in the structure I am using. Like why the submanifold as a warp product, why as an ambient metallic Riemannian manifold. And then in the third section, I talk about my result. So due to the time restriction, it is not possible to discuss whole the presentation. So I will skip the first two, that is about the structure I am using. So I will skip to the third section directly. So let us start the presentation for the curvature from the curvature invariant. Curvature invariant play a key role in the differential geometry as well as in the physics. For instance, the magnitude of the force required to move an object at a constant speed is, according to the Newton's law, a constant multiple of curvature trajectory. Second, the motion of a body in a gravitational field is determined by the curvature of a space-time according to Einstein. So before starting the presentation further, I would like to recall the NAS much celebrated, the NAS embedding theorem. So what was that theorem? Every Riemannian manifold can be isometrically embedded in some Euclidean space with sufficiently high codimension. Now question is, in this theorem, what was the aim of Nash? So let us see, actually, with the help of in this theorem, NAS was aimed for in hope that if a Riemannian manifold could always be regarded as a Riemannian submanifold. This was the aim of NAS theorem. But unfortunately, this would actually what happen if it will happen, then this will yield the opportunity to use the extrinsic help. But this hope had not been materialized till 30 years of the born of this theorem. Now, what was the difficulty? Why this theorem can't be materialized? So these are the few one. It requires very large codimension of the Riemannian manifold to admit an isometric embedding in Euclidean space in general. This is the first difficulty. Second one, the submanifold, the higher dimension are difficult to understand. Third one, there was no general optimal relation between the known intrinsic invariant and extrinsic invariant for arbitrary Riemannian submanifold of Euclidean space. Now question is, what was the possible solution? If these were the difficulty, what were the possible solution? So here comes the solution. One need to introduce new type of Riemannian invariant different in nature from the classical invariant. So, and the second was one need to establish general optimal relation between the main extrinsic invariant and new intrinsic invariant. So motivated by this and overcome these difficulties, Chen introduced new type of Riemannian invariant and established general optimal relationship between the extrinsic invariant and intrinsic invariant of the subnet. And this relation is also known as Chen's inequality. So what is the main aim of this presentation? The aim of the presentation to obtain the Chen's inequality for warp product submanifold in metric product space, to discuss the equality case of the inequality obtained, and third one to discuss some application in terms of the harmonic function and Hessian functions. So here we come first result of our work. Let M be an n-dimensional warp product theta slant submanifold of an m-dimensional locally metallic product space form. Then we obtain the relation 17, where this delta and nebula are the Laplacian operator and the gradient on M1. And the equality case hold in this inequality 17 if and only if M is mixed totally geodesic isometric immersion and the relation H1 N1 is equal to H2 N2 holds, where H1 and H2 are the mean curvature vector along the M1 and M2. For the theory of integration, we recall that if M is orientable compact invariant submanifold, then for the volume element dV on M, we have relation 18. So using the fact in 18, we arrive at the following conclusion. Let 5-year compact orientable warp product theta slant submanifold in locally metally product space form. Then the submanifold is simply Riemannian product if and only if we have the relation 90. Next result is let M be the n-dimensional warp product theta slant submanifold on m-dimensional locally metallic product space form. Then if the warping function M is harmonic function, then the inequality 20 exists. The last application we have discussed in the article else in terms of the Hessian function. So let phi be the positive C infinity differentiable function, then the Hessian tensor of a function phi is a symmetric two covariant tensor field on M defined by 21 such that the 22 holds. Where this component of the Hessian function can be expressed as in expression 23. So as it cons, the next result we have obtained in terms of the Hessian function. Let M be an n-dimensional warp product theta slant submanifold of m-dimensional locally metric product space form. Then the inequality 24 exists. So that's all about the presentation side of the results. These are the few references we have used. Thank you so much.
Thank you, Dr. Akif. Thanks a lot for such a nice presentation. Any questions? Professor Afsos wants to ask something. Sir, you can ask. Okay. Okay. So we'll proceed further. The next presenter is Dr. Anu Devgan. A brief introduction of Dr. Anu Devgan is she did her BSc and MSc from Punjab University, Chandigarh, and her PhD from Punjabi University, Patiala. She has attended many conferences and presented many papers. She has around 3 years of teaching experience. Her title of presentation is Development of Semi-Riemannian Geometry. Dr. Anu Devgan, you can present your talk.
Hello. Good evening, everyone. Sir, actually, I'm unable to connect it by laptop. Can I deliver it using my mobile phone? Because it's showing all.
Yes, you can use mobile, but share the screen.
Okay, okay, no problems. Yes, I'm connecting. Yes, yes. Yes, sir. Wait a minute. Yes, yes.
Ma'am, you have 10 minutes. Huh?
Yeah,
Please
yeah. No problem.
finish your talk within this 10 minutes.
Yes, sir. Yes, sir. Yes. Oh, wait a minute. Good evening, everyone. Since we are myself, Dr. Anu Devgan, thank you for giving me a chance to participate on this platform. Am I audible? Hello? Am I audible? Yes. Okay.
Proceed.
So, yes. These are the contents of my presentation, starting up with introduction, then preliminaries, and then the main results. Abstract. In this talk, the main objective is to discuss about the development of semi-Riemannian geometry. Riemann introduced the notion of sectional curvature for a Riemannian manifold, and it generalized the Gaussian curvature for surfaces in R3. We have derived the expression for the Riemannian curvature tensor of an indefinite Kähler manifold with Norden metric. Next to it, the characterization of holomorphic sectional curvature to the setting of an indefinite, almost complex manifold with knot and metric has been extended. Yes, sir.
Ma'am, your presentation is not visible. Please share the screen.
Okay, wait a minute. I'm sharing my screen. With the screen. Start now. Okay. Is it fine now?
No, ma'am, it's not visible.
Now is it visible?
No.
Should I connect it again or something like that? Wait. Stop video share.
It is not visible, ma'am.
Wait. Now?
No.
Screen. Is it now?
Not yet, ma'am.
I'm allowing, but I don't know why it is not visible. Now it's my video. I have to share my screen, right? So I have to go to Google.
Open your file and then
sharing,
share it.
but I
Open
don't
your
know why
file.
it's not Yeah, wait a minute. Yeah, this is my PDF file. I have opened it. Now I have to open with.
Share it.
Now?
No.
Hello? Now?
No, madam.
Ma'am,
Not
it is not visible. You can conclude your talk by just your conclusion part, whatever you know, you just present orally. It's okay. You take 2-3 minutes and finish it.
Is it possible I should email my presentation to Majid Ali
Yes.
and he'll? Huh?
Yes, you can email to the convener. It's okay, no problem.
Okay, I'll conclude the main results. Fine. In this, I'll try my best, but I don't know why I'm not getting connected because I got the password and everything. But sir, my main results are in this. Actually, I'm defining the curvature properties of Riemannian metric, and I have worked out with Northern metric in this case. And in the case of Northern metric, actually that product comes out to be negative, right? So when the product comes out to be negative, is it fine now? Is it visible now? Still not?
Not visible. You continue and finish in 2-3 minutes, madam. Just.
Okay. So we work out on the.
Are you sharing your screen?
Yes, sir. I'm sharing my screen. Would anybody please direct me how to do it?
Right below there is a green button which says share screen next to chat. Can you see that? There's a share screen right below this window where you see all people logged in. Zoom window. There is one green share screen.
If you are unable to present your work now, you can email us and we will present from here.
This is the drawback of Zoom meeting.
Yeah.
Documents are to be shared in Google Meet. Whole screen is shared.
Yeah.
I think, madam,
Yes,
thing
sir.
to
Yes,
share
sir.
screen.
Yeah,
Go,
yeah.
go in share and share the document. Then it is
Yeah.
visual.
I'm going in share. Then I have to go
And
to my document. Okay.
Your
Yes.
PDF. Share your PDF.
Yeah.
Then it is
No.
visual.
Is it fine now?
Yeah. Yes.
Okay.
Yeah,
Okay.
it's okay. Now
Okay. Okay, now I'll go to my main results. Okay. So, this is the content of my presentation. Well, non-Euclidean, just give me 5 minutes. I'll sum it up. Okay. Sorry for the delay. Well, the non-Euclidean geometry considers spaces where Euclid parallel postulates fail. So she said it for the first in 1733, and then later on there are so many people or geometers who have contributed a lot in this theory. In modern theory of manifolds, these notions correspond to manifolds with negative and positive curvatures respectively. So historically, the development of differential geometry is credited to Gauss and Riemann, and the focus of this geometry was to measure the distance in angles of manifolds. Now, before proceeding further, what do you mean by Riemannian manifold? This is a basic definition of Riemannian manifold. I guess everybody is well off of this. In this paper, we are working on basically light-like manifolds. So there are the three types of vectors: space-like, time-like, and light-like. This is the light cone. In this paper, I'm considering both the types of manifolds that are, one are almost complex manifolds, which are even dimensional, and the other one is almost contact manifolds, which are odd dimensional manifolds. We have calculated the curvature. Well, this is the definition of an almost complex structure. Next one, this is the definition of an almost Hermitian manifold, that is G bar of Gx, comma Gy is positive of G bar of Xy. In my paper, we have worked on almost complex manifold with Norden metric, and in this case, the equation 1 represents, this has come out to be negative of G bar Xy. So therefore, our work is somewhat different from the earlier almost Hermitian metric, right? And we have two metric, and the other metric is G tilde bar, which is equals to G tilde bar of Xy is equals to G bar of Jx comma Jy. Equation number 2. And both the metrics are indefinite of nature. Well, similarly, almost contact B manifolds are also defined in this form. Here also we have a difference of a negative sign, and because of that negative sign, we are getting so much different geometry. Well, these are the basic definitions. Now coming up to the main results, we have the curvature tensor R is of this form. And so for case of holomorphic sectional curvature, you know the sectional curvature for a non-degenerate plane spanned by xy is given by equation number 13. And if hx is always positive with constant with respect to any unit vector, then m is said to be of constant holomorphic sectional curvature at a particular point m, a small m belonging to capital M, and since hx is constant, that depends on this, so sometimes we denote it by Cm. Now, in our theorem, we have defined it like this. So firstly, we have calculated this, expression for the Riemannian curvature, which comes out to be as equation number 14. That is R of x, y, z, w is equals to this equation. And then we have defined in theorem that says that if M bar be an indefinite almost complex manifold with Norden metric satisfying equation number 15, then R of x, jx, x is proportional to alpha x plus beta jx, where alpha and beta are the functions of holomorphic sectional curvature hx for every tangent vector x at that particular point M in M bar. Next is for a constancy of holomorphic sectional curvature for the bisectional curvature, that is if R of x j bar x is equals to 0, then for every null vector this h of x hy is equals to negative of minus h of xy. And then for constancy of phi holomorphic sectional curvature, we have also proved that this theorem holds true for the odd dimensional case too, and this is the theorem. So this is all what I have. These are the main results. Thank you so much for giving me time and having patience because I was not able to connect earlier. Any questions?
Thanks a lot, ma'am. Thanks a lot for your presentation. Any questions? Next presenter is Dr. Abdul Malik Muhammad.
Thank you so much. Thank you.
Abdul Malik Muhammad, are you available? Abdul Malik Muhammad. Okay, as he is not available. Also, there is no representation of the Department of Mathematics, Manu. I request the convener to have a brief talk in his specialization, because he is a master in differential geometry. He is specialized differential geometry. We are also having in our department. I request Dr. Majid Ali to present. Take 10 minutes, as we are requesting all to have only 10 minutes. Majid sir, hello.
Yes, sir. Actually,
please take 10 minutes and finish your talk so that we can start validating session in time.
Actually, it was not planned, and Khwaja Sahab has requested me. Our senior most faculty, Sayyid Najamul Hasan sir, also wanted me to present, but we had very packed schedule, so I did not fix any of my lecture over here. But as Khwaja Sahab has ordered me, so I had to obey him. Sir, please give me 2 minutes so that I can share my file.
सर
वालेकुम सलाम, क्या हाल है भाई?
जी सर अल्हम्दुलिल्लाह, आप कैसे हैं सर?
बस जी ठीक है, मजे बढ़िया।
Dr. Majid Saab, we can't hear you. Can see your slides.
Is it visible now? Is it visible?
Yes, yes, visible.
Okay. Thank you, Professor Fajr Moin Saab, for giving me this opportunity. Actually, this work is with Professor Adara Ambalaga. She is from Romania, and this work is involving inequalities for generalized, normalized delta Casorati curvatures of slant submanifolds in metallic Riemannian space form. Professor Sirajuddin has already given a brief introduction about slant submanifolds, so I need not to go much in detail. I will just put up my main results over here. In 1990, concept of slant submanifolds came into light from B.Y. Chen, and since then many geometers have used this notion of slant submanifolds in different settings. For example, in Euclidean space, B.Y. Chen; in hyperbolic spaces, again B.Y. Chen; in golden Riemannian manifold, it was studied by Bahadir and Sirajuddin; and in Sasakian manifold, it was Cabrioso. So, as far as golden Riemannian manifolds are concerned, M. Caresmanu and C. Redcano studied the golden structure on Riemannian manifolds in 2008. There has been an interesting work in the field of golden differential geometry. In 2013, notion of metallic structure as a generalization of golden structure defined on Riemannian manifold was pursued by the same authors. Recently, different aspects of metallic Riemannian manifold concerning curvature have been discussed in so many papers. On the other hand, B.Y. Chen introduced Chen's invariant, and this is basically a tool to study relationship between intrinsic invariants and extrinsic invariants. So one major development was there. The traditional Gauss curvature was replaced by Casorati curvature by his famous in his famous work, and that led down the defining optimal inequalities.
Dr. Majid, scroll the PDF.
Oh, sorry, I'm coming to result basically. So F. Casorati gave us the tool to defining Gauss curvature as both principal curvature of surface in 3 are 0. So these are some preliminary things. So I may skip it. We have defined scalar curvature over here, and this is normalized scalar curvature. This is norm of second fundamental form. This is the Casorati curvature, which I was talking about, and these are the normalized delta Casorati curvature. Okay, so these two things were generalized to generalized normalized delta Casorati curvature, and basically we will be using these two things. Okay, so this is all about metallic Riemannian manifolds. We are having a polynomial of degree n and satisfying this criteria. So if Px is satisfying x square plus 1, that is almost complex structure. In this case, it is almost product structure and so on. So this is what we say, the m-dimensional manifold which is satisfying this phi square p phi plus qi is said to having metallic structure, and a Riemannian manifold having metallic structure is known as metallic Riemannian manifold. If we put P and Q to be 1, then this manifold reduces to golden Riemannian manifold. So we can skip all these things over here. We have constructed this one example over here, so we are skipping this thing also. This is all about slant sum manifolds in metallic Riemannian manifolds. This is the curvature identity. We have a curvature locally Riemannian manifold we considered like that, and on that we had metallic structure. So this is the Riemannian curvature tensor for locally Riemannian manifold having metallic structure and dot on it. So this is the main result. Supposing the slant sum manifold are immersed in locally metallic Riemannian manifold, then generalized normalized delta Casorati curvature satisfies this inequality. Again, generalized normalized delta Casorati curvature del cap C satisfies this curvature, and equality in 3.1 and 3 holds if n is invariantly quasi-umbilical. If we consider this frame field E1 to En plus 1 to En, basically this one is the tangent frame and this one is the normal frame, then this is the equality case. So if all shape operators satisfy this criteria. So this is the proof. We can basically skip over here. So we can skip the proof part. But one can see, because this work has already been published in Journal of Geometry. So one can see the proof from there. This is the particular case of main result, and we have the normalized delta Casorati curvature satisfying these two inequalities, and this can be easily concluded from the main result. So the main result, theorem 3.1 gives us so many applications. Basically, we have, if we put theta to be 0, we have the same result for anti-invariant sum manifold and so on. Theta is 0 invariant and theta pi by 2 anti-invariant in slant sum manifold. So these are some of the applications of the main result. So all these. One more thing is there. We should discuss over here. If we put P and Q to be equal to 1 in our main inequality for metallic structure, then we will be obtaining golden structure. If we put P equals to 2 and Q equals to 1, we have silver structure. If we put P equals to 3 and Q equals to 1, we have bronze structure. And if we put P equals to 4, Q equals to 1, subtle. For P equals to 1, Q equals to 2, copper. P equals to 1, Q equals to 3, nickel. I must mention over here that golden number, from where we have taken the inspiration and the golden structure was defined, is said to be one of the famous number in mathematics, and it has application in every branch of science and social sciences also, architecture, everywhere where you will find golden number. So these are some of the references. And I must be thankful to Raja Saab for giving me this opportunity and representing my department.
Thank you, Dr. Majid Ali Chaudhary. Thanks a lot. This session is also open for any questions, if any. If no questions, then we can proceed quickly towards valedictory session. I thank all the presenters of this session for their excellent presentations. I request all to switch on their camera so that we can have a screenshot. switch on your cameras. Please, we can have a screenshot. Subhashji.
Yes, sir. Done, sir.
Okay, okay. Thank you, all of you. I request all who are online to be connected for a few more minutes. We are starting valedictory session. The chief guest for this valedictory session is Professor Zafar Hassan, sir. I think Professor Zafar Hassan's personality does not require any introduction. Sir, please wait for a few minutes. I request the convener of this session to take the mic and tell brief report about this symposium.
Okay. Thank you very much, sir. Actually, it's very difficult task to summarize this symposium because very renowned debaters were there who delivered their talks over here, and I'm just a student before all of them, and still I'm learning a lot of things. But as Raja Saab has asked me to present the report, so actually overall we had 13 invited talks in the symposium, and our session started with the very first talk of Professor Afsoos Ali Sheikh. Professor Afsoos Ali Sheikh talked about geometry of solitons, and the main theme of his talk was about quantum conjecture. So then he developed some theory about Ricci Filo and presented very beautifully how the theory of Ricci solitons developed. The next talk was delivered by Professor Mohammad Bel Khalfa. He talked about Ricci's pseudosymmetry of complex Q spaces and the notion of complex Q spaces analog to Q space in real geometry. The third talk was by Professor Zafar Hassan, and he actually collected and gave us a very deep understanding of Ricci solitons, and that was very important lecture delivered by renowned Professor Zafar Hassan sir. And we learned a lot of new things about Ricci solitons, their developments, and what the current research are being, or developments or investigations are being done by different geometers nowadays. The fourth lecture, which technically was shifted to today itself by Professor Sirajuddin Saab, and he just summarized recent developments on slant manifolds and their applications. And as I'm a student of geometry, I know how important slant manifolds are. So he basically gave an idea about slant manifold, their applications in warp product in different ambient spaces. The next talk was by Dr. Sudhakar Kumar Chobe from Oman, and he talked about FRT gravity and solitons. So somehow it happened that the first day was just for Ricci solitons itself. So next talk was by Professor Mehmet Akif Akyol from Turkey, and he talked about Riemannian maps, and particularly he emphasized on pointwise Riemannian maps. And it was really nice talk by him. He presented so many examples, and it was a very nice thing to see, because there are abstract results, but when we give some example, so newcomers also can understand those things. So it was very beautiful lecture. Next was by Professor P.K. Sahu from BITS Pilani Hyderabad campus, and he talked about wormholes in exponential FRT gravity. And particularly, I learned a lot of things from this lecture and how to connect geometry with all these things. And he talked a lot of things about astrophysics, stellar astrophysics, about the dark sector of the universe, and so on. So it was really, and he also talked about Einstein-Hilbert gravitational Lagrangian. So we all know Einstein-Hilbert space form. So all of our working in semi-Riemannian manifolds, and we know semi-Riemannian metric has were constructed when they were working to obtain an example of negatively curved surfaces. So Einstein-Hilbert gravitational Lagrangian was studied by Professor P.K. Sahu. Next was from Professor Belgiali from Algeria, and he gave us a tool basically, and it's very important in the aspect because we need a tool to connect between Kanmatsu manifold and Sasakian manifold. So up to dimension 3, Professor Belgi, I must be thankful to you that you gave us this tool. How can we compare these two things? Because up to now we were understanding that there's no connection, but you gave us a tool to connect these two things separately. Okay. The next thing was from Professor Sudhir Kumar Srivastava from Gorakhpur University, and he talked about gravitational collapse. And this lecture was so basic that even graduation or PG student can understand it very well. So the next invited talk was from Dr. Najrul Islam Khan, invited talk number 10. And he talked about metallic structure. Fortunately, I am also working on metallic structure. So, and metallic structure nowadays has number of applications. So, and metallic is shown differential manifold and its frame bundle. This is very important, tool to study frame bundle, tangent bundle, and so on. So it was a very nice lecture. Next was from Professor Vishnu Narayana Mishra, and he gave us some tool to approximate, the polynomial curve and curve surfaces. Actually, Bézier curve is very important in the sense because we have some applications in computer design and computer geometric design. So directly we can have some applications, and a person who is doing computer design or computer geometric design can go to robotics and automobile industry. So this lecture was very interesting in this sense. Next, in this list, we had Dr. Rakesh Kumar. As the young geometers know, and Dr. Rakesh Kumar has published several papers in light-like theory, and his group is working very hard as far as light-like geometry is concerned. So he talked about geometry null hypersurfaces of Lagrangian manifolds with rigging technique. So Dr. Rakesh emphasized on rigging techniques, and it was very interesting to listen to him. Next lecture was from Professor Adela Mihai. Adela Mihai. So Professor Adela Mihai talked about rectifying curves, and this lecture is important in the sense because it's very basic thing. If we understand rectifying curves, then we go to the manifold because curves is a one-dimensional manifold. So she delivered the lecture in such a way that it was she presented in such a way that even BSc student can understand the things. So thank you very much, Professor Adela, for delivering such a nice talk. There were some contribute talks also. So on behalf of organizing committee, I apologize that due to paucity of time, we couldn't give enough time for our contributory speakers. Although there was very interesting lecture. For example, Dr. Danish Siddiqui, he talked about relativistic space-time with magnetic energy momentum tensor. So it has many applications in physics, and everybody knows this. Dr. Mubin Ahmed from Integral University, he talked about LP Sasakian manifold admitting star eta Ricci Yaml solitons. So again, yes, solitons, Yaml solitons, it has number of applications. So it was a very nice lecture. Dr. Ram Shankar Gupta, on the other hand, talked about biharmonic hypersurfacic satisfying Laplacian of H equality with lambda times H in pseudo-Euclidean space. So next was from Dr. Alia Nar Siddiqui. It is the study of statical submersions. As we know, the submersion is very important in the sense, and this leads us to the field of information geometry. Then next was from Kamran Khan, Dr. Kamran Khan from Aligarh Muslim University. He talked about sequential warp products and manifolds in nearly Taylor manifolds. And Dr. Sushil Shukla on light-like hypersurface on indefinite Sasakian space form. And Dr. Inan Onal from Turkey, he talked about some semi-symmetric condition on Taylor manifolds. So all of them were very nice lectures actually, and I cannot summarize them in 1 or 2 or 3 lines, but I'm sorry I have to do so. So next was from Dr. K. Fasihi Ramandi, a fine metric geometry application to relativity. This talk was directly related to relativity, and it has number of applications basically. Agijan Bahadur, Dr. Agijan Bahadur, on the other hand, examined the golden structure from a different perspective, and he presented not only golden manifold but also metallic manifold, because metallic manifolds are generalization of golden manifolds. So, and he also talked about statistical manifolds as an application. Dr. Musafir Ali, his lecture is very nice in the sense that he also talked about a eta Ricci solitons, and he analyzed LP Kanematsu manifold and space times. So it has applications as far as relativity is concerned. So now the last but not least, the second last was from Dr. Sabina. She studied curvature properties of Morris on wormhole met. So it is also application part basically, and she attributed all the result very nice way. So then Muhammad Akif, Dr. Muhammad Akif, he presented some pinching results for warp products manifolds in locally metallic product space form. Warp product is very important to read in order to study space time. So in the sense it was then Dr. Anu Degan. So development of semi-Riemannian geometry. She due to some technical reasons she couldn't present in time, but she managed, and it was very nice lecture. So with this, I finish this concluding remark, and I must say that all of the lectures were delivered very nicely, and I have no words in order to thank basically, because I cannot summarize 1, 2, 3 lines. All of them were the wonderful lectures, and I personally learned a lot of things, and people will be agreeing with me at this point. So thank you very much, Khwaja sir, for giving me this opportunity. Thank you very much.
Thank you, Dr. Majid Chaudhary, for such a detailed report about the symposium. Now I request Dr. Afroz, Head Department of Mathematics, to say a few lines about this symposium. Dr. Afroz, sir.
Thank you, Dr. Khwaja Saab. The sun that rises has to set, flowers that bloom have to glue, as in the same way the program begin has to end. A big thanks to everyone who joined International Symposium on Differential Geometry and its applications. I also express my sincere thanks to speakers from abroad and our country to make this program successful with their valuable presence, such as Professor Zafar Hassan Saab, Professor Afsoos Ali Sheikh, Professor Muhammad Bel Khilfala, Professor Sirajuddin, and many more. I also thanks to our PBC Professor S.M. Rahmatullah and Dean School of Sciences who were present in the inaugural session. I also thankful to our all faculty members and research scholars who have been working from last 20 days to make the symposium successful. I also express my regards to each and everyone who put equal efforts to make it big and successful. Thanks to all once again. Thank you very much.
Thank you, Dr. Afroz. Now I request Professor S.N. Hassan sir to say a few lines about this symposium. Professor Hassan sir.
Thank you, Dr. Khaja Manaji. It was a wonderful experience, 2 heavy days, but wonderful days. And differential geometry is a subject which gives us a very deep understanding into the nature of mathematics and some of the very deepest questions, like the first lecture which we had by Professor Afsoz Ali Sheikh, where he spoke about the Poincare conjecture. It gives us a very deep understanding of the nature of mathematics, nature of space and time, and obviously some of the fundamental questions from cosmology, the nature of our space and time and relativity are answered here. These 2 days we had, I'm sure our students have experienced the power of differential geometry, and they were patiently sitting and listening to all the lectures delivered by experts from all over the world. We have gone through 2 years of pandemic, of being locked up in our homes, but the better part of this thing was that we have learned that there is a virtual platform where great minds can come across different nations without having to go through the problems of getting permissions, visa permissions, traveling across borders, but we can come on this platform and exchange our views and ideas. I'm very happy that senior people like Professor Afsoz Ali Sheikh, Professor Ehsan, and Professor Mohammed Belkhaf Khelfa were present in most of the talks, and they were listening to the young speakers and encouraging them and very critically analyzing the talks. And I thank the head of the department, Dr. Afroz, and the Dean of School of Sciences, Professor Salman Khan, for having given a platform or given the permissions at the right time to Dr. Majid Ali Chaudhary to conduct this wonderful workshop. And I should mention here that Dr. Subhash Ala had been toiling throughout all the time, standing by the side of Dr. Majid Ali to get this whole thing done. It was a wonderful experience for me too. It took me through manifolds, which I probably studied in my master's. There were excellent lectures on the Ricci spaces, Ricci curvatures, and then solitons, and all the way to wormholes and the singularities which we get in stellar evolutions and black holes. So with this, I would request that some of the participants express their views about this meeting. And the credit goes to Dr. Majid Ali for having arranged such a wonderful seminar. And I hope we have many such seminars in School of Mathematics. Thank you.
Thank you, Professor S.N. Hassan. Now I request Professor Zafar Hassan sir to deliver the presidential remarks for this session. And I am sure that he requires no introduction. Professor Zafar Hassan sir.
Bismillahirrahmanirrahim. Very good evening to all of you. So let me thank once again giving me another opportunity to share my views about this symposium. It was a wonderful symposium, and most of the session I have attended. Only today in the morning I was busy, so I could not attend some sessions. But anyway, it was a very nice symposium. And all the credit goes to the organizers, the head of the department, as well as the dean and the senior faculty member, Professor Hassan. They all worked very hard to organize such a nice symposium. So now this is this is some sort of a different event in the sense that usually in conference we have all types of subjects, all disciplines are covered. But here we have a symposium. Symposium always means it is considering only one topic. So everybody was either from geometry or from relativity. Even the people who were from relativity, they were using the geometric techniques of differential geometry. So it was a very nice symposium. In 2 days, 13 invited talks were given. So it is a wonderful thing that Majid somehow or the other collected all the persons from all over the globe, persons from Turkey, Saudi, Romania, Iran, Algeria. They came to us in this symposium and they share their ideas with us. So it was a very nice experience. And one thing I don't have to say about the lectures, because it has been very well summarized by Majid himself in his concluding remarks. Almost he has covered all the abstracts of the invited talks as well as some contributed papers. So it was a very nice thing. More people, those who are worked in differential geometry, they covered the pure aspect of the differential geometry. And those who were working in the application part, they apply the techniques of differential geometry to relativity or to the modern theories of gravitation or to the wormhole, or how they can understand the structure of wormhole, dark energy, dark matter, and so on. So it was just a coupling of geometry as well as physics. So if you look at the Einstein equation, the left hand side says that Rij minus half Rgij equal to the right hand side k times Tij. So left hand side is purely geometric. Rij, the Ricci tensor, it is a geometric quantity. R is the scalar curvature. This is also a geometric quantity. And G, metric tensor, of course, it is a geometric quantity. So the whole left hand side is a geometric quantity. On the right hand side, we have some constant times Tij. Tij is the energy momentum tensor. So right hand side is the physics. So this was the actually dream that of the Einstein. He wanted to geometrize the whole physics. So now here you will see the combination of geometry and physics as well. Both the things have been coupled in this one symposium. So this is a very wonderful thing that you people have done it very successfully. So I congratulate to all of you all for organizing such a nice event. And I am sure that Manu will organize regularly these type of symposium and conferences in future also. Now the things are open. Slowly and slowly the universities are getting open and offline classes are going on. So I'm sure next time when Manu will arrange a conference, it will be an offline conference so that the persons from the abroad or from the other part of the country, they can see the beauty of Manu as well as the beauty of Hyderabad city. I've been there for some time, so I know the people there in Manu. They are very nice people, very nice infrastructure is there. And of course, they are very hardworking people. So I'm sure that under the new leadership, the Manu will flourish more and more. One more thing I want to say here, this is what I have noticed in this seminar, that most of the participants, they belong to my family tree. My family tree is, I worked with Professor Syed Izhar Hussain. So I am his second student. Professor Hassan Shahid is his student. Hassan Shahid's student is Majid is with you. And Gupta is also there. Ram Shankar Gupta is also Hassan Shahid's student. My student Musafir take part in this one. Another student of Professor Hussain was Waqar Azam Khan, whose student Kamran Khan has presented his paper in this symposium. Another student of Professor Hussain was Rakesh Nakai's. Rakesh Nakai's student Rakesh was there. He presented, not only gave a invited lecture, but also chaired a session. And Rakesh's student also present there. So some sort of my family tree was present there. So I'm happy to see that at least my geometry group is working very nice, very well. They are doing very well. And for this, at least I am proud of. I'm proud of every lecture, but in particular, I am proud of this Majid, Rakesh, and Musafir, of course. They are doing wonderful job. They are doing very nice work. And I'm sure with the help of such symposium, they will learn a lot of more. They know how to deal with the complex problems. So I again give you all my good wishes to all of you. And I am also thankful to all the participants, all the invited speakers, all the contributors who presented their paper, as well as all the listeners who listen online. So it is a very nice experience that in online case, what you can do, somehow you can sleep from the class also. You do some work and then again come here and see. While offline class, it is very difficult to leave the classroom where the lecture are going on. So this is the benefit of online classes. Anyway, so I'm once again thankful to all of you to giving me an opportunity to share my ideas. So I wish you all the best. Good luck to all of you. Be happy and take care of yourself. Thank you. Thank you very much.
Thank you, sir. Thanks a lot for your inspirational thoughts. Lastly, I request Dr. Majid Ali Chaudhary, convener of this symposium, to present vote of thanks. Dr. Majid. Oh, अच्छा, आवाज नहीं है क्या?
Unmute करिएगा sir.
Thank you, sir. Thanks a lot for your inspirational thoughts. Lastly, I request Dr. Majid Ali Chaudhary, convener of this symposium, to present vote of thanks. Mute, sir.
Thank you very much, Dr. Khwaja Muhyiddin Sahab. But before I present my vote of thanks, I may be requesting some of the guests and some of the speakers to share their feedbacks or say something or say some comments about the symposium. So session is open. So if anybody wants to say something,
yeah. Bismillah. First of all, I would like to thank you very much for the invitation first, for this opportunity, and for organizing an interesting and wonderful conference. It was perfect mix of topics, geometry and physics, and also from different, we say, generalization of researchers, junior and senior researchers from different universities from India and abroad. Wishing to all happiness, life, good health, success, and for others, Ramadan Mubarak. Wishing you blessed and happy Ramadan. See you, inshallah, in the next future. Assalamu alaikum. Thanks a lot.
Walaikum assalam. Happy Ramadan to you also.
Thank you. Thank you.
Anybody else who wants to say something?
Invite कर लें बंदे को, जो बंदा मौजूद हो उनको उसको invite कर लें. Just invite the person who is present there.
Anyone willing to present feedback, please?
You just ask somebody. Some person from Turkey is there. Danish is there. You can ask them to say few words. Just call them by name.
Okay. Danish bhai, would you like to say something? Professor Belji Ali, Professor Unal, Professor Afsosh Ali Sheikh is there.
Thank you very much. It was a very nice conference. I'm very happy to be here. There are very good subjects which are from differential geometry and theoretical physics. I think we will read all these papers to obtain new results. Thank you very much for this good organization, and happy Ramadan to everyone. Thank you.
Okay, thank you very much, sir. Professor Belji Ali, Dr. Rakesh Kumar, Dr. Alexandro, Professor Absosh Ali Sheikh.
Yes. Hear me?
Yeah, please. Dr. Rakesh Kumar. Dr. Danish, you want to say something?
Assalamu alaikum. First of all, I would like to congratulate to all the, especially Dr. Majid and his team, organize such a wonderful event and provide us a platform during this 2 years tough time, and share our ideas about the geometry, relativity, and its applications. So I'm hoping that inshallah next time there will be another event like that, and we will see you once again. Thank you very much, and happy Ramadan to all.
इंटीग्रल में थे सब, इंटीग्रल की सारी पार्टी सऊदी में पहुंची, जजान में सब
Okay. Now I request Dr. Majid Ali Chaudhary to present both of thanks. Dr. Majid, sir.
Okay. Thank you, sir, for calling me for presenting vote of thanks. Assalamu alaikum and good evening to all of you. Thank you is such a prayer that cannot be seen or touched. It must be felt by heart. I feel honored and privileged to get the opportunity to propose a vote of thanks on this special occasion. I would like to thank all the participants from throughout the world who blessed us with their online presence. I'm also very much thankful to all program advisory committee members and the invited speakers, especially Professor Absosh Ali Sheikh, Professor Muhammad Bel Khalfa, Professor Jafar Hassan, Professor Sirajuddin, Dr. S.K. Chobe, Dr. Mehmet Akif Akyol, Professor P.K. Sahu, Professor Belji Ali, Professor S.K. Srivastava, Dr. Najrul Islam Khan, Dr. Rakesh Kumar, and Professor Habil Adela Mihai. Words are not enough to thank you. Words are not enough to thank your constant guidance and support to shape the symposium. I, on behalf of organizing committee, convey deep regards and hearty thanks to our Honorable Vice Chancellor, Professor Syed Ainul Hassan. I'm also thankful to Professor Pro Vice Chancellor, Professor Rahmatullah Saab, and Registrar Manu, Professor Ishtiaq Ahmed Saab. They helped us in obtaining the necessary administrative approval for organizing the event in our campus. They supported in all possible manner to organize this conference. My special thanks to Professor Salman Ahmed Khan, Dean, School of Sciences, Manu, for various helps we received towards this conference. My sincere thanks to Professor Syed Najmul Hassan Saab, the senior most faculty, for his help and support at various stages. Today, my words are not enough to express the gratitude to him, sir. Sir, thank you very much, sir. I would like to thank our beloved head of the department, Dr. Afroz, for his constant help and guidance that radiated a source of energy within us. We will ever remain grateful to you, and we thank you for being with us today. Thank you, Dr. Afroz. Last but not least, I would like to thank my colleagues, Dr. Subhash Ala sir, our technical guru. Of course, your technical guru Subhash sir, for all his constant support throughout the program. I take this opportunity to thank Dr. Khwaja Moin Saab, our elder brother, Dr. Sayyid Wasim Raja Saab, and all other colleagues of the School of Sciences for their kind support and encouragement. An event of this dimension cannot happen overnight. The wheels start rolling months in advance. We have been fortunate enough to be backed by a team of very motivated and dedicated PhD scholars. I cannot thank everyone enough for the involvement they have shown and the willingness they have expressed to take on the completion of tasks beyond their comfort zones. Mr. Basharat Hussain, Mr. Ishfaq Ahmed Malla, Mr. Asif Badar, Mr. Tahir Manzoor, and Mr. Abdul Hamid Kahwa. I have no words that are enough to thank you. Without you guys, this event was not possible. Thank you very much again. If time is money, then today you have spent millions for us. Thanks to all of you for making this event successful. Have a wonderful evening and thank you very much. Now, I hand over this to Khwaja Moin Saab. Moin Saab, it's to you now.
Thank you, Dr. Majid. This session ends here. I, on my behalf and all from the department, thank you all. Thanks a lot for attending the session. Thank you.
Thank you.
Everyone.
Thank you, everyone. Thank you.
Thank you.
So we can.
Okay, see you then. Okay.
Bye.
Okay. Assalamu alaikum. Fi amanillah.
في أمان الله. نعم تمام.
Thank you very much, everybody. Thank you very much and happy Ramadan.
Happy Ramadan to you.